Toyota Land Cruisers are built on ruthless and high-precision production lines that weld and torture test every chassis before it earns the badge. From robot arms shaping high-strength steel to engines inspected for longevity and frames flexed to the limit, this is manufacturing built for survival. In this video, we go straight onto the floor to watch a Land Cruiser go from raw metal to off-road legend. The story of the Land Cruiser's creation begins long before the first bolt is fastened or the first body panel is stamped. It starts with design intent, precise engineering blueprints, and a commitment to quality control that informs every choice along the production line. Before even a single part enters the assembly plant, Toyota engineers have spent years developing the latest Land Cruiser model. Using computer-aided design systems, crash simulation software, and off-road test labs to validate every frame weld, axle articulation angle, and suspension rebound setting. These simulations and pre-manufacture analyses create the digital foundation upon which the physical vehicle will be built. Now, when we arrive at the factory, typically one of Toyota's dedicated SUV production plants, such as the Tahara or Yoshiwara plant in Japan, we're greeted not by the roar of chaos, but by a carefully orchestrated ballet of steel, robotics, and human oversight. This factory is more than a collection of machines. It's a living system, optimized for repeatability, efficiency, and above all, zero-defect manufacturing. The first physical component of the Land Cruiser to be created is the frame. Unlike unibody vehicles that integrate body and frame into one structure, the Land Cruiser is built using a full ladder frame chassis, a hallmark of serious off-roaders and heavy-duty trucks. This ladder frame starts its life as a series of precisely cut and formed steel sections, each made from high-strength, hot-rolled steel that arrives at the plant in massive coils. These steel coils are unrolled and fed into CNC-controlled stamping and cutting machines that shear the metal into the required dimensions for the side rails, cross members, and mounting brackets. Once these components are formed, they move to the frame welding station. Here, an array of industrial welding robots, suspended from gantries and articulated arms, descend upon jigs that hold each piece in place with sub-millimeter precision. These jigs are crucial. They ensure that each frame is square, symmetrical, and dimensionally accurate to fractions of a millimeter. Using MIG and MAG welding techniques, the robots trace complex bead paths, fusing the frame together with a consistency that only automated systems can deliver. After each frame is welded, it undergoes dimensional scanning using laser measuring systems, which compare the physical result against digital blueprints in real time. Any variance is flagged immediately and either corrected or discarded, depending on severity. From here, the raw frame undergoes an extensive surface preparation process. It is conveyed through an immersion tank line where it's degreased, cleaned, and dipped in an anti-corrosion phosphate coating. This is followed by a cathodic electrodeposition primer bath, commonly known as e-coating, where an electrical current bonds anti-rust primer to every exposed surface of the frame, even inside enclosed box sections. Once coated, the frame is baked in a curing oven to harden the primer layer, forming the first shield against corrosion that the Land Cruiser will face in its lifetime. Meanwhile, in a parallel part of the factory, body components are being fabricated. These include the outer shell, roof panels, doors, hoods, and tailgates. Each component is stamped from galvanized steel sheets using a massive press line. These presses exert thousands of tons of force to transform flat metal sheets into complex, three-dimensional shapes in just seconds. Every panel must emerge with zero warping, perfect contours, and clean edges. Here again, quality control is relentless. Vision systems scan each panel for wrinkles, cracks, or inconsistent radii. These individual panels are then conveyed to the body shop, where robotic arms perform spot welding to assemble them into what's called the body in white, a complete, unpainted car body without any moving parts. Unlike the frame, which is welded largely by robots, the body in white assembly involves a mix of automation and skilled manual welding, particularly in complex joint areas where human adaptability still outperforms machines. Workers in specialized welding suits and helmets double-check robotic welds, perform precise manual tacks, and insert structural adhesives that bond key stress points for added torsional rigidity. Once both the ladder frame and body in white are complete, they proceed along separate lines toward eventual integration, but not before the body receives its finish. This takes place in the paint shop, a fully enclosed and environmentally controlled section of the plant where air filtration, humidity, and temperature are all tightly regulated. The body is first cleaned in a multi-stage wash tunnel, then passes through a second E-coat dip tank, identical in principle to the one used for the frame. After curing, the body moves through a sanding and inspection stage where workers dressed in white lab-like uniforms hand sand each panel to create a flawless surface for painting. Next comes the paint booth. Here, electrostatic spray robots apply multiple layers of base coat and clear coat, often in high-end two-tone or metallic finishes. These robots mimic human movement with incredible dexterity, able to reach deep crevices while maintaining a uniform paint thickness. Between coats, the body passes through baking ovens to cure each layer, producing a deep, resilient finish that can withstand the harshest climates, whether desert, jungle, or tundra. As the body is being painted, attention shifts to the Powertrain assembly line. The Land Cruiser's engine is a marvel of durability engineering, often a turbocharged V6 or robust, naturally aspirated V8, depending on the model year and market. These engines are assembled in a dedicated engine plant, either nearby or in a regional facility. Engine blocks are cast from aluminum or iron alloys, then machined with extreme precision to form cylinders, crankshaft seats, and oil galleries. Assembly teams install pistons, crankshafts, camshafts, timing systems, and cylinder heads, each torqued and timed to tight tolerances. Every engine is then hot tested using a dynamometer, simulating real-world loads to verify compression, torque, emissions, and idle behavior. Once validated, the engines are sent to the main vehicle assembly plant, where they await union with the transmission, either a rugged automatic gearbox or a manual transmission for certain utility models. These are coupled to the engine via robotic clutch alignment and torque checking machines, ensuring concentric balance and zero runout. The completed powertrain is then lowered onto a moving subframe, which also includes the front and rear differentials, transfer case, and drive shafts. At this point, we reach one of the most iconic moments in Land Cruiser production, the marriage process. This is when the body and frame finally come together. The fully painted body in white is carefully lowered onto the rolling chassis by a massive overhead gantry system. Workers align frame mounts with precision machined body bushings and use pneumatic tools to torque heavy-duty bolts to exact specifications. This moment is both symbolic and practical. It's the point at which the Land Cruiser becomes more than a collection of parts. It becomes a single, cohesive machine. With the body now secured to the ladder frame chassis, the Land Cruiser has taken on its distinctive silhouette, but it remains little more than a shell with a skeleton. To bring this vehicle to life, the next phase involves the precise installation of its drivetrain, suspension, and electrical nervous system, a process that combines brute mechanical assembly with intricate wiring, calibration, and testing, all executed on a constantly moving assembly line. Once the marriage process is complete, the vehicle is conveyed via automated guided carriers to the suspension installation zone. Here, factory technicians install the front and rear suspension assemblies onto the mounting points integrated into both the chassis and subframe. The Land Cruiser, unlike crossover SUVs, is designed for real-world abuse and off-road articulation, so its suspension is often built around independent double wishbone geometry in the front and a multi-link solid axle or live axle setup in the rear, depending on the variant. The suspension components arrive as pre-assembled modules: control arms, coil springs or air suspension bags, dampers, stabilizer bars, and mounting bushings, all staged in precise sequence. Using robotic torque arms and hydraulic lifts, technicians align and fasten each assembly to the vehicle's mounting brackets. Torque settings are tightly controlled and digitally monitored using torque sensing tools that immediately signal if any fastener is under or over tightened. This is especially critical on a vehicle like the Land Cruiser, where off-road stress loads can be severe, and even the smallest flaw could lead to long-term durability issues. Following suspension installation, the axles and drive shafts are connected. These link the differentials, already installed on the frame during powertrain subassembly, to the wheel hubs. Front and rear prop shafts are aligned and bolted to their respective flanges using flexible couplings that allow articulation without transmitting vibration into the chassis. The transfer case, which enables the vehicle's four-wheel drive capabilities, is now electronically linked to the vehicle control system using waterproof harnesses, which are clipped into place along the underbody routing channels. In the adjacent station, the brake system comes to life. Calipers, brake discs, hydraulic lines, and ABS wheel sensors are pre-installed on knuckle assemblies and now joined to the master cylinder and vacuum booster at the front of the vehicle. Every brake line is fitted using anti-corrosion coated clips and rubber grommets that isolate vibrations and prevent wear. After installation, the brake system is filled with fluid using an automated vacuum fill machine that ensures the lines are completely purged of air, critical for consistent pedal feel and braking performance. Sensors verify fluid pressure and pedal actuation force during a quick bench test before the vehicle moves on. As the mechanicals begin to solidify, another equally vital process unfolds in parallel: the installation of the vehicle's wiring harnesses and onboard electronics. Modern Land Cruisers have extensive electrical systems, covering everything from engine management and safety systems to multimedia interfaces and off-road terrain response modules. The primary wiring harness is a massive, branching structure composed of thousands of color-coded wires bundled by function and destination. This harness is laid manually into the body shell by trained technicians who follow a strict sequence and routing path. Each connection is marked by a QR code or barcode that technicians scan to verify proper fit and location. The harnesses are clipped into custom-molded plastic retainers, and junction boxes are secured in the engine bay, cabin, and underfloor areas. Grounding points are torqued to chassis connections, and fuse boxes are populated with model-specific fuses and relays. By this stage, the Land Cruiser's central nervous system is beginning to form, ready to carry data, commands, and electrical current to every corner of the vehicle. Next comes the fuel system. A large, impact-resistant polymer fuel tank is mounted under the rear chassis rails using steel straps and dampers. This tank has internal baffles to prevent sloshing and is equipped with level sensors, pressure regulators, and a high-flow electric fuel pump. Once installed, quick connect fuel lines are clipped to the underbody routing paths and connected to the engine's fuel rail, with multiple pressure checks verifying that the system is sealed and ready for operation. At this point in the line, attention shifts to the interior, an area where Toyota applies as much precision as it does to mechanical systems. The bare cabin, still painted but unadorned, now receives layers of insulation, padding, and trim components. Sound deadening mats are applied to the floor pan using heat-activated adhesive rollers, followed by thermal insulation sheets placed along the firewall and under the roofline. These materials are crucial in creating the Land Cruiser's signature interior quietness, especially in rugged environments. Once the insulation is laid, flooring components such as the carpet, footwell liners, and underseat padding are installed. Technicians then mount the dashboard assembly, an enormous, complex component pre-built at a substation with integrated wiring, HVAC vents, infotainment screens, and control buttons. The dashboard is robotically guided into position and bolted to the firewall using multi-axis torque arms, ensuring a perfect alignment with side panels and center console structures. The steering column is next. It includes electric tilt and telescoping motors, a collapsible shaft for crash safety, and electronic interfaces for steering angle sensors and driver assistance systems. It's fitted from below and torqued to both the firewall and dash crossbar. Following this, the front seats are wheeled in on trolleys and installed using locator pins and power connectors that automatically link heating, cooling, and adjustment motors into the body harness. Rear seats, cargo trim, door cards, and overhead components follow, each snapped and bolted into place with pre-assembled clips and hardware. Moving further down the line, the door assemblies, painted, glazed, and pre-trimmed in an earlier stage, are now mated to the body. Large articulated robots or specially designed lift assist rigs help align the heavy doors to their hinges. Once bolted into place, technicians adjust each door for flush fitment using feeler gauges and laser guides to ensure panel gaps are within tolerance. Power window motors and locks are connected and tested in real time. At this point, exterior fittings begin. The front grille, headlights, taillights, bumpers, and fender flares are installed. The Land Cruiser's lighting system is particularly complex, involving adaptive LED arrays, daytime running lights, and integrated washers for certain models. Each component is wired, clipped, and sealed with weatherproof gaskets to ensure long-term durability in wet or dusty environments. Sensors for parking assist, radar cruise control, and blind spot monitoring are installed behind trim panels, with calibration to follow in later stages. The wheels and tires, often rugged, all-terrain types with reinforced sidewalls, are mounted next. These are torqued using automatic nut runners that measure clamping force electronically. Wheel alignment is then performed using an advanced, laser-guided system that adjusts toe, camber, and caster values to factory specifications. This step ensures the Land Cruiser will track straight and true from the first meter of use. Now, with a fully assembled interior, powertrain, suspension, and exterior, the Land Cruiser reaches the electrical testing and fluid fill stations. Here, every onboard system is powered up and scanned using a diagnostic tool plugged into the vehicle's onboard data port. Over 150 sensors and modules are queried for error codes. Air conditioning is filled with refrigerant. The power steering, coolant, transmission, and differential oils are pumped into their respective reservoirs via closed-loop filling systems that eliminate contamination. Each fluid fill line has inline flow meters, digital volume counters, and pressure regulators to ensure precise volumes are administered, with system pressure monitored for anomalies. Technicians conduct function tests on HVAC controls, infotainment systems, dashboard illumination, reverse cameras, and audio systems. Even the seat memory buttons are activated to verify motor control and data retention. As the Land Cruiser nears final assembly, it undergoes a simulated ignition. The engine is started for the first time, and technicians listen for abnormal vibrations, rattles, or leaks. Exhaust gas sensors verify emission compliance, and drive-by-wire throttle response is tested under load. The vehicle is driven onto a rolling road dynamometer where automated systems simulate various road conditions to test acceleration, braking, and driveline engagement. With the mechanical assembly now complete and the engine having roared to life for the first time, the Land Cruiser enters a critical phase of its production journey: quality validation and final inspection. At this point, every system is functional, but the factory's role is not merely to assemble parts. It is to confirm that each individual Land Cruiser meets Toyota's legendary standards of durability, safety, and refinement. This is where precision testing, calibration, and simulation converge to ensure that not a single flaw escapes into the real world. The vehicle first proceeds to the final inspection conveyor, a slow-moving belt surrounded by inspection bays and quality control technicians. Here, the vehicle is subjected to a comprehensive visual and tactile inspection. Under bright, uniform lighting conditions and mirrored surfaces designed to expose even the slightest ripple or scratch, skilled workers scan the painted body panels for cosmetic perfection. They run gloved hands over each surface, checking for texture inconsistencies, orange peel effects, or trapped particles under the clear coat. Special attention is paid to panel gaps and alignment. Each door, hood, and tailgate is opened and closed repeatedly to ensure smooth operation and consistent shut lines. A precision feeler gauge is used to measure the distance between adjacent panels at multiple points, confirming that they fall within Toyota's strict tolerances, often less than 3 mm in variance. Any deviation triggers a corrective rework, often involving panel realignment or trim replacement. Inside the cabin, technicians perform a fit and finish audit, systematically checking every touchpoint, seam, and surface. They press every button and knob, ensuring proper tactile feedback and response. Seat adjustments, steering wheel tilt, and telescoping mirror positioning, and window operation are verified. Even cabin lighting is checked, not just for function, but for uniformity in color temperature and intensity. Every HVAC vent is opened and closed. Cup holders are tested for resistance and rattle, and storage compartments are opened to confirm smooth latching and retention. Next, the Land Cruiser undergoes a leak and weatherproofing test in what's known as the shower booth or rain simulation chamber. This sealed room replicates an intense downpour, up to 50 litres of water per square metre per minute for several minutes, while the vehicle remains stationary. High-pressure nozzles blast water at strategic angles, covering the windshield, roof, door seals, hood seams, and underbody in a controlled, high-volume spray. Inside, sensors and technician observers watch for any signs of water intrusion. Paper strips are laid in door sills and on floorboards to detect even the slightest moisture. If a leak is discovered, the vehicle is flagged and pulled off the line for immediate resealing and retesting. It cannot proceed until it passes the rain test with zero leakage. This step is especially crucial for a vehicle like the Land Cruiser, expected to withstand deep water crossings and monsoon conditions around the globe. Once water testing is complete, the vehicle is dried using high-volume air dryers and microfiber towels, then passed into the dynamic testing line. This portion of the plant is built like a miniature test track and includes a chassis dynamometer, suspension shakers, and NVH test chambers. The vehicle is driven onto rollers that simulate different road conditions: smooth asphalt, coarse gravel, cobblestones, and even railroad-like rumble strips. Sensors embedded in the seat rails, firewall, and steering column measure vibration amplitudes and frequencies. Technicians inside the cabin listen and feel for buzzes, squeaks, or rattles, often called BSR defects. These can originate from loose trim clips, misaligned panels, or improperly torqued fasteners. If a defect is detected, it is logged, and the vehicle is removed from the line for diagnostic teardown and correction. The expectation is not simply that the Land Cruiser should function, it must feel cohesive and solid, like a single carved block of steel, even when driving over rough terrain. Following dynamic tests, the vehicle undergoes wheel alignment and headlight aiming. On a laser-guided platform, cameras scan each wheel to measure camber, caster, and toe angles. Adjustments are made to the suspension arms or steering links via automated or technician-guided tools until alignment falls within specifications. Proper alignment is vital not only for tyre longevity and handling performance, but also for safety systems like lane keeping assist, which depend on accurate steering angle input. Headlights are tested and aimed in a separate chamber equipped with photometric sensors. The Land Cruiser's LED or projector headlights are precisely leveled and oriented to ensure they illuminate the road correctly without blinding oncoming drivers. Adaptive lighting functions are activated and checked for smooth operation, whether swiveling into corners or dimming individual LED segments during oncoming traffic. From here, the vehicle moves to the ADAS calibration zone, a critical step in preparing modern vehicles for road use. Advanced driver assistance systems, such as automatic emergency braking, lane departure warning, adaptive cruise control, and pedestrian detection, require that cameras and radar modules are perfectly aligned and calibrated. In this dedicated bay, high-resolution printed targets and reflective calibration boards are positioned at precise distances from the vehicle. The onboard systems scan these targets to calibrate the field of view, depth perception, and horizontal axis of the forward-facing camera and millimeter wave radar units. Any error in calibration can lead to inaccurate distance measurement or false triggering, so the process is repeated multiple times and verified using test data. The calibration results are uploaded to a central database that tracks the configuration history of every vehicle produced. This data can later be accessed by dealerships during servicing, ensuring traceability and long-term system accuracy. Now that every system is validated, the vehicle proceeds to the final software, flashing and configuration bay. This is where the Land Cruiser's onboard ECU cluster is updated with the most recent firmware, software maps, and region-specific settings. This may include engine management tuning for specific fuel grades, transmission behavior mapping, infotainment localizations, navigation system data, and wireless communication protocols such as Bluetooth, Wi-Fi, or connected services. At this stage, factory technicians also activate region-specific compliance features such as emissions readiness flags, alarm system settings, and telematics modules, depending on the target market. Each configuration is verified with a scan tool and signed off electronically, with the software build number recorded in the vehicle's internal logs. Only now does the Land Cruiser approach what is known as the final release gate. This is the symbolic and operational point at which the vehicle is officially deemed complete. The engine is shut off, the ignition keys are programmed and paired to the immobilizer, and the factory build manifest is printed and affixed to the dashboard. Every vehicle is tagged with a VN, barcoded for traceability, and matched to its build sheet, which includes options, colors, production dates, and destination data. Before the vehicle exits the factory floor, it passes through a dedicated detailing and protection zone. Here, trained specialists give the vehicle a final clean, polish, and inspection under soft lighting. Protective plastic films are applied to vulnerable surfaces like door sills, bumpers, infotainment screens, and seat cushions to prevent damage during transit. The tires are overinflated slightly to accommodate potential temperature or pressure changes during storage or shipping. Depending on destination, vehicles are either driven under their own power to a nearby staging lot, loaded onto enclosed transport trucks, or, more commonly for international orders, driven onto open-sided auto carriers headed for port. Some models are even driven short distances onto roll-on roll-off cargo ships where they're carefully parked and secured by maritime handlers. Toyota's global logistics system then routes each vehicle to the appropriate country, dealership, or fleet customer, with continuous tracking from the moment it leaves the factory. With the Toyota Land Cruiser now fully assembled, inspected, and officially cleared through the final quality gates, its departure from the factory marks not an end, but the beginning of an extraordinarily managed logistical operation. Every vehicle that rolls off the production line is immediately tagged for traceability and assigned a specific post-factory journey depending on its model variant, trim level, destination market, and regional compliance standards. This downstream supply chain is as complex and meticulous as the assembly process itself, ensuring that every Land Cruiser reaches its customer without compromise. The first stop for many newly built Land Cruisers is the factory's outbound vehicle staging area, an expansive, organized expanse of tarmac where hundreds of vehicles are arranged in neat rows, each aligned with specific shipping designations. From here, Toyota's Vehicle Logistics Control Team coordinates batch deployments of finished units either to inland dealerships via transport trucks or to international ports by rail or by direct carrier convoys. In Japan, for instance, production centers like Tahara or Yoshiwara route large volumes of Land Cruisers to export terminals in Nagoya or Yokohama. These vehicles are often earmarked for overseas regions such as Australia, the Middle East, Africa, or North America, markets where rugged off-road capability is highly valued and thoroughly tested. But before these vehicles are loaded onto ships or trucks, they undergo port preparation processes that further ready them for transport and market compliance. Many Land Cruisers, especially those headed abroad, are sent to a vehicle logistics center adjacent to the port. At the VLC, they undergo a multi-step check involving additional accessory installation, protective film removal, and localization. In this phase, market-specific options that cannot be practically installed on the main assembly line are added. These might include tow hitches, roof racks, side steps, navigation system SD cards, language packages, or customer-requested extras like off-road kits, underbody protection plates, or integrated dash cameras. All installations are performed by certified technicians using torque-verified tools and original parts. Any deviation from standard configurations is meticulously documented to preserve the vehicle's warranty and certification status. Equally important is the post-assembly compliance verification. Each region around the world has unique emissions, safety, and equipment requirements, and Toyota manages this through VN-specific programming. For example, a Land Cruiser bound for the United States must meet federal motor vehicle safety standards, California Air Resources Board regulations, and NHTSA labeling, while one going to the UAE must be equipped with Gulf-specific cooling systems, stronger alternators for heat tolerance, and Arabic language infotainment settings. Once localized and cleared, the vehicles are lined up for Ro-Ro shipping or loaded into multi-level vehicle transporters, depending on whether they're being exported overseas or moved overland. Ro-Ro ships, purpose-built for automotive logistics, feature vast internal decks that resemble floating parking garages. Each vehicle is driven onto the ship under its own power, guided up loading ramps and secured to the deck using industrial tie-downs. Toyota limits engine runtime during this stage to reduce emissions and fuel consumption, and each vehicle's onboard diagnostics are scanned one last time before the cargo bay is sealed. While en route to their destinations, Land Cruisers are tracked using global supply chain visibility platforms that integrate with GPS and customs data systems. Estimated time of arrival, environmental exposure logs, and any transit anomalies are recorded to maintain full accountability. In the case of sea freight, average journeys can last anywhere from 7 to 45 days, depending on distance and port congestion. Throughout that time, Toyota's regional distribution hubs prepare to receive, inspect, and redeploy the incoming vehicles. When a shipment of Land Cruisers reaches its destination country, it undergoes a pre-delivery inspection at a regional Toyota import processing center. Here, the vehicles are unloaded and immediately examined for any cosmetic or mechanical damage incurred during transit, such as scuffs, dings, or tie-down abrasion. Battery voltage levels are tested, tire pressures are corrected, and all protective films and covers are removed. A diagnostic scan confirms system integrity, firmware versions, and mileage. Even the odometer reading is logged to ensure compliance with regulations about mileage disclosure. At this stage, additional final touches are added. Owner's manuals, registration documents, floor mats, and dealer-branded accessories are placed inside the cabin. In some regions, local emission or safety stickers are applied, and temporary license plates are affixed for legal transport to dealerships. Once cleared, vehicles are grouped by dealer destination and loaded onto regional delivery trucks that will carry them directly to showrooms. Back at the dealership, the Land Cruiser receives one final inspection, this time by the sales and service staff, who perform a customer-facing version of the PDI. They check for cosmetic perfection, start and idle the vehicle, activate climate controls, sync the infotainment system with local maps and language settings, and validate that no error codes have appeared since transport. Only once this process is complete does the vehicle become available for customer viewing, test drives, or delivery. But even after the vehicle reaches its owner, the story of the Land Cruiser's production process continues. Part of what makes this model so revered is the rigorous pre-production durability testing and engineering validation that underpins its design, much of which occurs far from the public eye, long before mass production begins. Toyota's quality assurance team performs global field testing of pre-production Land Cruisers in some of the harshest environments on Earth. These are not just theoretical validations. They are full vehicle stress tests that replicate real-life torture scenarios. Endless hours of corrugated dirt roads, deep water fording, freezing temperatures, desert sand climbs, and sustained towing at maximum payloads. Test mules are equipped with telemetry and stress sensors embedded into suspension arms, chassis, weld points, engine mounts, and transmission casings. Engineers collect terabytes of data across thousands of miles of field testing, looking for signs of fatigue, thermal breakdown, or structural deformation. Some of these test vehicles are subjected to frame twist tests on purpose-built platforms that simulate extreme diagonal wheel articulation. Others are parked in cold chambers for overnight freezes, and then started without preheaters to evaluate cold start behavior and electronics resilience. Brake systems are stress tested down alpine gradients with full payload, while fuel systems are evaluated in high-altitude passes to ensure vapor lock prevention. Every component, from seat foam density to door hinge lubrication, is analyzed, tested, and reworked if it fails to meet Toyota's standards. Once the prototype phase ends and the production design is finalized, Toyota invests in a global supplier quality control network to ensure consistency across all materials entering the factory. Every bolt, sensor, harness, and panel delivered to the Land Cruiser production line must meet ISO TS 16949 and Toyota's own global supplier requirements. These parts are tagged with barcodes and batch numbers that trace their entire life cycle, from material sourcing to delivery. In the event of a future defect or recall, Toyota can pinpoint the exact day, shift, and supplier lot that produced the affected component, allowing for rapid response and recall management. Even paint batches, foam chemical blends, and adhesive curing cycles are tracked in real time. Many Land Cruiser parts are over-engineered compared to industry norms. For example, frame cross members are often hydroformed, resulting in stronger yet lighter weld-free shapes. Fasteners on critical joints are not only torqued, but angle-checked with digital sensors to ensure the proper stretch and clamp force. This over-engineering is not excess, it's strategic durability. And in keeping with Toyota's core philosophy of Kaizen, or continuous improvement, feedback from real-world usage informs future iterations. Engineers regularly review warranty claims, service center data, and owner feedback. If patterns emerge, such as premature wear on a bushing or corrosion on a bracket, adjustments are made on the production line, sometimes within days. This responsiveness is one reason why even aging Land Cruisers remain reliable long after newer competitors have faded. As the modern factory evolves, so too does the way the Toyota Land Cruiser is built. While the foundational principles of reliability and mechanical toughness remain unchanged, the methods by which these values are achieved have transformed dramatically over the decades. In this next phase of the journey, we step deeper inside the plant, not just to observe physical assembly, but to understand how the Land Cruiser benefits from one of the most advanced manufacturing ecosystems in the automotive world. At the core of Toyota's approach is the Toyota Production System, a manufacturing philosophy built on lean principles, just-in-time delivery, jidoka, and continuous improvement, or Kaizen. The production of a Land Cruiser represents one of the most intricate expressions of TPS in action, balancing high-mix, low-volume builds with exacting consistency. Unlike high-volume sedans or economy cars, Land Cruisers are often built to order, customized by region, and produced in lower quantities, demanding exceptional flexibility from the factory floor. That flexibility is enabled by Industry 4.0 technologies, a suite of digital tools and automated systems that allow each vehicle to be uniquely tracked and built in sequence. As soon as a Land Cruiser order enters the system, a digital production order is generated and encoded into what Toyota calls the build manifest. This manifest travels with the vehicle in both physical and digital forms, informing every workstation along the line exactly what variant is approaching, the trim level, drivetrain layout, regional settings, colors, accessories, and emissions package. Throughout the factory, a network of programmable logic controllers and manufacturing execution systems orchestrate operations with incredible coordination. These systems communicate with RFID readers, barcode scanners, and vision recognition cameras that constantly monitor each vehicle's movement and configuration. Robotic arms that apply adhesive, install glass, or torque bolts adapt automatically depending on the model variant passing through. This seamless shift between configurations enables Toyota to build a diesel-powered Land Cruiser for the Australian Outback on the same line as a petrol V6 bound for a Middle Eastern fleet customer, without ever shutting down or retooling the line. In the welding shop, cobots, collaborative robots, work side by side with human technicians. While fully automated welding cells handle repetitive, high-speed tasks like frame seam welds or floor pan spot welding, more complex and nuanced joints are still guided by experienced hands. The cobots assist in holding parts, adjusting positioning, or applying filler materials, responding to slight shifts or tolerances that may not be visible to machine vision systems. These robotic helpers improve efficiency without replacing human intuition, an essential balance in Land Cruiser production. The paint shop is another showcase of cutting-edge automation. Here, electrostatic rotary bell atomizers precisely control paint flow and dispersion, resulting in incredibly fine droplets that adhere more evenly and waste less material than traditional spray systems. The robotic arms in this area are capable of mimicking human wrist and elbow movements, adjusting in real time based on vehicle height, curvature, and even ambient temperature or humidity. Every body is scanned before and after painting using laser profilometry, which maps the surface for thickness uniformity, gloss level, and micro defects invisible to the naked eye. But even with all this automation, Toyota continues to rely heavily on human craftsmanship, particularly in the trim and final assembly zone. Here, skilled workers, many of whom have decades of experience, perform tactile evaluations and intricate installations that machines still cannot replicate. These technicians are trained through Toyota's in-house Takumi development program, a mentorship model where junior assemblers learn directly from master-level craftspeople over years of apprenticeship. One example is seat upholstery. While much of the seat frame assembly is robotic, the final wrapping of leather or synthetic material is done by hand. Each seat is inspected for tension, uniformity, stitching consistency, and padding distribution. The goal isn't just functionality, it's comfort and luxury underpinned by durability. In markets like the Middle East, where sand, sweat, and heat stress interiors more aggressively, even the grain of the leather is tested for UV resilience and moisture rejection. Other critical human-controlled operations include dashboard alignment, door hinge installation, and seal compression fitment. These may sound minor, but in a vehicle expected to operate in extreme environments, the margin for error is virtually zero. An improperly seated door seal can lead to wind noise, water leaks, or dust ingress, issues that would tarnish the Land Cruiser's otherwise sterling reputation. Technicians use soft mallets, torque wrenches, and custom fit gauges to confirm that every joint, hinge, and gasket is within specification. In the realm of electronics and diagnostics, Toyota employs AI-assisted test benches to simulate hundreds of driving scenarios. As each Land Cruiser nears the end of the line, it is plugged into a comprehensive vehicle communication interface that links all onboard control modules to a centralized diagnostic system. Artificial intelligence algorithms analyze sensor outputs for anomalies, looking not just for outright failures, but for subtle trends that could indicate a future issue. For example, a window motor that draws slightly more current than average may still work perfectly, but the AI flags it as a possible early-stage failure, and the part is replaced before the vehicle ever leaves the factory. AI also plays a role in predictive maintenance of factory equipment itself. Every robotic joint, spray nozzle, and conveyor belt in the plant is outfitted with sensors that monitor usage cycles, vibration levels, temperature, and wear patterns. These data streams feed into a digital twin of the plant, a virtual model that mirrors the real-world state of every machine. When a critical component shows signs of fatigue or misalignment, the system alerts maintenance teams well before a breakdown occurs, minimizing downtime and preserving output quality. All these systems, robotic, digital, and human, work in concert within the framework of Toyota's Genchi Genbutsu philosophy, meaning go and see for yourself. Engineers, supervisors, and even executives are required to visit the factory floor regularly, interact with staff, and observe production firsthand. This cultural commitment ensures that management decisions remain grounded in reality and aligned with the conditions experienced by those who build the vehicles. The cumulative result is not just a product that's rugged or capable, it's a vehicle built with an awareness of its purpose, and a factory tuned to produce that outcome consistently. The Land Cruiser's legendary reliability is not an accident of design. It's the end product of thousands of discrete quality control decisions made at every junction in the factory's ecosystem. And Toyota's commitment doesn't end at the physical vehicle. Increasingly, post-sale digital infrastructure is integrated during production. Infotainment systems are loaded with over-the-air update capability, and telematics modules allow for remote diagnostics, GPS tracking, and performance monitoring. These systems are calibrated on the line and verified during end-of-line testing, setting the stage for ongoing connectivity and customer engagement long after delivery. Our journey begins deep within the steel supply and stamping operations, far from the glittering finish lines of final inspection. The G-Class starts life as a collection of raw, flat metal panels. These panels, primarily high-strength steel, are delivered to the facility in massive coils, which are unrolled and leveled before being fed into industrial press machines. These presses apply thousands of tons of pressure to shape the steel into the various foundational parts of the G-Class body, such as the floor pan, door skins, roof frame, and iconic flat body panels. The unibody shell is not used in the G-Class. Instead, it's built with a ladder frame chassis, a method more common in heavy-duty trucks. This makes the process both more rugged and more complex, requiring each piece to be perfectly formed to exact tolerances. Once the panels are pressed, laser-guided robotic arms trim and smooth the edges with astonishing precision. Each cut is planned digitally down to the 1/10 of a millimeter, ensuring uniformity across thousands of units. Now we move into the body-in-white phase, the initial stage of structural assembly. Here, the stamped panels are arranged into sub-assemblies. The floor pan, side frames, firewall, and roof supports are meticulously aligned on a series of jig fixtures. These large, articulated steel mounts hold each piece in perfect position for welding. But unlike many modern car factories where robot arms zip through spot welds in a blur, the G-Class body is largely welded by hand. Dozens of skilled technicians, each highly trained, wield welding torches in a choreographed dance of sparks and heat. More than 6,000 welds are performed on each body, reinforcing the vehicle's structural rigidity. As they go, workers constantly inspect joints visually and mechanically using go-no-go gauges to confirm tight fits and ensure that structural integrity is never compromised. The welding process is a symphony of patience and expertise. Welders must account for heat distortion, managing the order and location of each weld to maintain the geometric accuracy of the body. They use pneumatic clamps, steel rulers, and laser levels to ensure that the angles and lines of the body remain true. It is here that the G-Class's signature upright posture begins to take shape. Those vertical window frames, slab-sided doors, and angular corners that give the vehicle its commanding silhouette. They're all defined and locked into place during this early phase. Once the body is fully welded and structurally complete, it undergoes a process known as metal finishing. This is where skilled craftsmen examine every seam, edge, and panel for imperfections. Small hammers, abrasives, and filler tools are used to smooth out inconsistencies. The goal is to achieve a surface that will accept paint without a single visible ripple or deformity. The attention to detail here is extraordinary. What may seem like an invisible bump to the naked eye will be caught later by paint defects if not resolved. Technicians in this stage often use high-powered overhead lights and fingertip inspection techniques to feel for irregularities. And yes, they still do it by touch. Technology can detect misalignments, but it's the trained human hand that often finds the smallest flaws. Once the body in white has passed inspection, it is ready for paint preparation. But before any color is applied, the shell undergoes a rigorous cleaning process. It is first immersed in a series of chemical baths, alkaline cleaners, degreasers, and deionized water rinses that strip away all traces of oils, residues, or contaminants from the welding and finishing stages. Then it moves into the e-coating process. This is where the body shell is dipped into a giant electrocoating tank filled with anti-corrosion primer. An electrical current is applied, causing the primer to bond to the metal surface at a molecular level. Every nook, crevice, and corner is coated evenly, providing unmatched rust protection. The G-Class was originally built for military duty, and this durability-focused philosophy continues today. After the e-coating, the body is cured in an oven at temperatures around 180 degrees Celsius. The curing hardens the primer and sets the foundation for the paintwork that will follow. Then comes the application of the base coat, color layers, and clear coat, each sprayed meticulously in high-tech painting booths. The factory offers a broad range of colors, from conservative blacks and silvers to vibrant custom finishes from the G Manufacture Personalization Program. Incredibly, many G-Class vehicles receive their paint by hand spraying, not automated robots. This allows greater control and customization for two-tone finishes, matte effects, and hand-masked accents. The painted body then returns to another round of inspections. Factory workers use light tunnels and soft cloths to detect even the smallest specks of dust, paint sagging, or orange peel textures. If needed, technicians wet sand and polish the affected areas manually. This is one of the most time-consuming parts of the process, but it ensures that the G-Class leaves the paint shop with a flawless, mirror-like surface. With the body now painted and prepped, attention turns to the chassis, the rugged ladder frame that defines the G-Class's off-road DNA. Unlike unibody cars, where the structure and body are fused, the G-Class separates these two elements, a design that offers superior strength and modularity. The chassis is fabricated from thick-gauge steel and welded into a rectangular framework with multiple crossmembers and mounting points. It's engineered to endure extreme torsional loads from uneven terrain, rock crawling, and high-speed travel over unpaved surfaces. The entire chassis is then treated with a special powder coating that protects it from gravel, salt, moisture, and mechanical wear. At this point, the chassis begins its mechanical assembly. Giant overhead conveyors lift it into place on a moving assembly line. Suspension components are added first. The G-Class uses a double wishbone front suspension and a rigid rear axle with trailing arms and coil springs, all designed for articulation and ride comfort. Workers mount control arms, install air or coil springs depending on the configuration, and torque each fastener to precise specs using digital torque wrenches that record every application for quality traceability. Drive shafts, differentials, and the transfer case follow next. The G-Class features 3 locking differentials, front, center, and rear, making it one of the most capable factory off-roaders ever built. These components are pre-assembled in sublines and arrive at the main chassis line just in time for installation. Each differential is bench tested before being mounted, and once installed, hydraulic and electronic connections are secured and checked for sealing integrity. Next, the engine and transmission arrive. These powertrains are built separately, typically at Mercedes powertrain facilities, and delivered fully dressed with wiring harnesses, fuel systems, and control modules already in place. A robotic hoist lowers the engine and transmission into the chassis as technicians bolt it down to reinforced subframe mounts. The transmission tunnel is lined with heat shielding and the exhaust system is connected. Stainless steel manifolds, catalytic converters, and mufflers are all aligned with laser guidance systems to ensure proper clearance and vibration isolation. As the powertrain is secured, attention turns to the braking and steering systems. High-performance disc brakes with multi-piston calipers are installed on each wheel hub. Brake lines are routed with stainless steel fittings and then bled using automated vacuum machines to ensure a perfect seal and no air bubbles. The power steering rack is attached and aligned, and its fluid circuits are pre-flushed to remove any contaminants. At this stage, the chassis is essentially a rolling platform, ready to meet the painted body that has been traveling in parallel on a separate line. Continuing our journey into the heart of the Mercedes-Benz G-Class assembly process, we arrive at the moment of mechanical matrimony, a pivotal point known within the factory as the marriage. This step is one of the most anticipated stages in any automotive plant. But here in Graz, it carries almost ceremonial weight. The moment when the meticulously painted body is lowered onto the fully built ladder frame chassis transforms a collection of high-grade parts into what begins to truly resemble a finished G-Class. The process begins with both the body and the chassis arriving at the marriage station on two separate automated conveyor lines. Precision and timing are essential, as the chassis is lined up beneath the suspended body shell. A series of hydraulic lifts and alignment pins begin the delicate work of bringing the two together. Technicians verify multiple reference points using laser measurement tools to ensure the body mounts align perfectly with the corresponding points on the chassis. The process may appear straightforward, but in reality, the tolerances are extremely tight, within a single millimeter. Any deviation could lead to misaligned panels, noisy interiors, or handling inconsistencies. Once the alignment is verified, the body is carefully lowered using a multi-axis robotic gantry system. Specialized bushings are inserted between body and frame to absorb vibrations, and bolts are torqued down using synchronized electric torque tools. These tools not only apply the correct force, but also record each torque event digitally for traceability. In total, dozens of mounting points are secured during this stage, creating a permanent bond between body and chassis. With the vehicle now structurally complete, the next steps shift focus to the installation of electrical systems and interior components. The G-Class is known for its advanced technology, luxury appointments, and off-road capability, all of which require an intricate network of electronics. Wiring harnesses are delivered to the line pre-assembled and bundled according to specific vehicle configurations. Each harness includes connectors for power distribution, lighting, infotainment, sensors, airbags, and the drivetrain management system. Installation of these harnesses is done mostly by hand due to the complexity and variability of options in each vehicle. Workers snake thick bundles of cables through the body structure, routing them through the firewall, behind the dashboard frame, under the floor, and along the roof rails. Clamps and cable guides ensure the wiring remains secure and doesn't rattle or chafe over time. Diagnostic computers are connected at this stage to confirm continuity, check for shorts, and verify module communications over the vehicle's CAN bus network. While this is happening, the HVAC system is assembled and installed. This includes the heater core, evaporator unit, blower fans, and electronic control motors that adjust airflow and temperature zones. The G-Class features multi-zone climate control, so ducting is routed with exacting precision through the dash, footwells, and rear cabin areas. Once the climate system is in place, the dashboard sub-assembly is installed as a single module. This enormous component includes the infotainment screen, control buttons, ambient lighting strips, and the central air vents. Workers use vacuum suction lifts to guide the dash into place without damaging the painted surfaces or soft leather trim. Now comes one of the most craftsmanship-intensive stages in the entire production, the installation of the interior. Unlike many mass-produced vehicles that use synthetic fabrics and machine-mounted panels, the G-Class is fitted largely by hand, using real materials: leather, wood, aluminum, and piano black lacquered plastics. The seats are built separately and upholstered using hides that are individually inspected for imperfections. Skilled trimmers sew the leather together using double stitching patterns that match the exterior color or the customer's specification. Once finished, the seats are bolted into the vehicle with electronic seat module calibration to ensure proper memory function and lumbar support. Door panels follow next. These are assembled in parallel stations where components like speaker grills, switches, ambient lighting, and leather inserts are bonded together before being mounted. Each panel is carefully pressed into place and tested for fit, sound insulation, and tactile feedback. The sound of a G-Class door closing is legendary. an unmistakable mechanical clunk that speaks to solidity. Achieving this sound requires a precise interplay of hinges, rubber seals, door weight, and locking mechanism geometry. Carpeting, floor mats, headliners, and trim moldings are next. Workers stretch and press these components into place using heat guns and hand rollers to ensure wrinkle-free surfaces and tight fits. The sunroof assembly is dropped in from above and sealed with multi-layer gaskets to prevent leaks. All the while, every stage includes quality inspections using both visual checks and functional tests. Is the stitching even? Does the infotainment system respond instantly to input? Is the rear seat heating element warming to spec? These aren't afterthoughts, they're checked and verified at every step. With the interior mostly complete, attention now turns to the installation of exterior finishing components. This includes the lighting systems, trim pieces, bumpers, grills, and the wheels and tires. Headlights and taillights are delivered in sealed packaging and installed using torque-controlled tools to avoid over-tightening. Each lighting unit is powered on and subjected to an alignment procedure that ensures optimal beam projection. The G-Class often includes LED matrix lighting, so precise calibration is required to ensure adaptive lighting functions correctly on the road. The bumpers, both front and rear, are more than decorative. They contain impact absorbers, parking sensors, and, in some models, radar modules for adaptive cruise control. These systems must be aligned with the vehicle's central ECU and tested for accuracy. The grille, which houses the iconic Mercedes three-pointed star, is mounted next, followed by trim pieces such as side skirts, fender flares, and the protective body cladding that's especially important for off-road variants. Wheels and tires are mounted towards the end of this phase. Each tire is balanced individually before mounting to minimize road vibration. The G-Class uses either 18-inch or larger wheels, depending on the model, and all are fitted with performance all-season or off-road tires. Lug nuts are torqued in a star pattern and then double-checked by a second technician for safety. The signature rear-mounted spare wheel is added last, requiring special reinforcement brackets to support its considerable weight. At this point, the vehicle is externally and internally complete, but it hasn't yet proven itself ready for the road. That's where the end-of-line testing begins. First, each vehicle is rolled onto a chassis dynamometer for a systems check. This stationary rolling road allows technicians to simulate driving conditions without the vehicle leaving the factory. Engines are started and revved through a range of RPMs. The transmission is cycled through its gears. Braking systems are tested under controlled load. Onboard diagnostics scan every system for fault codes, and calibration values are adjusted in real time. Next, the G-Class is taken into the water testing booth, a sealed chamber where high-pressure water jets blast the vehicle from all angles. This simulates heavy rainfall and river fording to confirm that all seals and gaskets are intact. Doors, windows, the sunroof, and even antenna mounts are tested for ingress. Any leaks are flagged for immediate remediation. Following the water test, vehicles are subjected to a visual inspection tunnel with multi-angle lighting. Here, inspectors walk around each unit, examining body panel gaps, paint reflections, wheel alignment, and emblem placement. Mirrors are adjusted, wiper blades tested, and final protective films removed. Finally, the G-Class is driven onto a short test track, either inside or just outside the factory. This final road test includes a variety of surfaces: cobblestones, incline ramps, sharp turns, and slalom sections. Trained drivers listen for abnormal noises, feel for steering alignment, and evaluate ride quality. Any deviation from spec sends the vehicle to a special adjustment area for corrections. Only once all tests are passed does the vehicle receive its final factory seal of approval. Even then, however, the process isn't over. Depending on the destination, Additional country-specific requirements are installed. These may include compliance labels, GPS regional settings, localized safety equipment, and left or right-hand drive adjustments. Paperwork is finalized, including the build sheet, quality inspection records, and shipment documentation. The vehicle is then either driven onto a covered transport truck or loaded into a sealed container for overseas shipping. Now that the G-Class has completed its rigorous in-factory birth, a process involving welding, painting, assembly, and exhaustive quality checks, it embarks on the next critical phase of its journey: preparation for global distribution. This phase, though less visually dramatic than robotic welders or precision-aligned dashboards, is nonetheless a feat of coordination and logistics. The moment a G-Class rolls out of the Magna Steyr facility in Graz, Austria, it transitions from handcrafted engineering marvel to a globally positioned product, bound for showrooms, private collections, mountain trails, or inner-city avenues. But before it reaches any of these, there is still a tremendous amount of effort that goes into protecting, staging, and transporting each unit with the same care and attention to detail used in its creation. Once a G-Class vehicle has passed its final road test and received its full quality release documentation, it is driven under its own power to the staging area adjacent to the main plant. Here, specially trained logistics personnel begin the final detailing and protection process. Although the vehicle is fully finished, there is a layer of preparation necessary to ensure it survives the rigors of global shipping. Protective films are applied to sensitive areas: the hood, roof, door sills, mirrors, and corners of the bumpers are covered with temporary plastic guards that resist scratches, UV exposure, and road grime. The alloy wheels are often wrapped in foam liners or protective rings to prevent damage from transport straps or accidental impacts during loading. Interior surfaces are also shielded with plastic covers over the seats, infotainment screens, and floor mats. Every vehicle is now tagged with a unique, VIN-linked logistics barcode, which details its destination, shipping method, port of entry, and delivery window. This data is integrated with Mercedes-Benz's global tracking system, allowing every stakeholder, from plant logistics to overseas dealerships, to monitor the car's location in real time. Depending on its final destination, the G-Class may undergo additional region-specific programming. For example, a vehicle bound for North America will be loaded with US-specific emissions calibrations and compliance documentation, while one heading to the Middle East might receive enhanced climate control settings and reinforced dust filtration for desert conditions. Next, the vehicle is routed to one of several outbound transport modes. For European customers or regional delivery, G-Classes are typically driven onto covered car haulers, large multi-deck trucks designed to transport 6 to 8 vehicles at a time. These trucks have air ride suspensions to reduce vibrations and protect the delicate ride height sensors and chassis calibration. For vehicles headed abroad, the process is more elaborate. The G-Classes are driven into rail cars or loaded into intermodal shipping containers, which are then routed to seaports like Bremerhaven in Germany or Koper in Slovenia. At the port, each container or open deck vessel is handled with specialized cranes and ramps that minimize jostling. It is worth noting that many G-Class models, particularly Special Edition or G manufacture builds, are transported in sealed containers to prevent salt spray, sun fading, or theft. The voyage by sea can take several weeks. For example, vehicles headed to North America might pass through the English Channel, cross the Atlantic, and dock at ports like Baltimore or Brunswick. Once at port, they are processed through customs, emissions, and safety verification, all under the oversight of Mercedes-Benz regional distribution centers. Then comes a second round of quality control, sometimes called a PDI or pre-delivery inspection. This includes checking tire pressure, recalibrating navigation systems to the local GPS constellation, adjusting language and date formats, and inspecting the vehicle for any damage incurred during shipping. If a vehicle has traveled thousands of kilometers by rail, truck, and sea, this inspection is crucial to maintain the brand's reputation for perfection. Once cleared, the G-Class is dispatched to its final destination, a dealership, fleet customer, private buyer, or regional collection center. Even here, the aura of exclusivity surrounding the G-Class continues. Many buyers opt for specialized white glove delivery, wherein the vehicle is transported by single-car covered trailer and presented with ceremonial fanfare, unveiling cloth, branded key boxes, and sometimes a personal orientation session with a brand specialist. The delivery experience is designed to match the vehicle's pedigree. But beyond the logistics and visual pageantry, what truly makes the G-Class remarkable is that even after all of this effort, the vehicle is still, at heart, a rugged, off-road tool. Every single G-Class, whether destined for a downtown penthouse or a mining operation in Siberia, is built to the same foundational spec: full-time four-wheel drive, locking differentials, a 2-speed transfer case, and a ladder frame that could survive military deployment. That's the irony and the charm of the G-Class. It's capable of climbing a 45-degree incline, fording rivers, and navigating icy switchbacks, yet it will just as often be used to roll quietly over cobblestones in Monaco or park beneath luxury boutiques in Dubai. The factory doesn't know what fate awaits each G-Class, and it doesn't matter. Each one is engineered for extremes, regardless of how pampered its life may be. Now, let's take a moment to consider the people behind this machine. While many modern automotive factories are fully robotic and optimized for scale, the G-Class production line retains an unusually high proportion of human labor. Over 1,500 skilled workers at Magna Steyr contribute to its assembly, many of them having decades of experience with the model. Their knowledge, much of it gained through repetition, mentoring, and attention to the tactile feedback of materials, is irreplaceable. They know the right torque by feel. They can spot a millimeter-wide gap from across the room. In a time where artificial intelligence and robotics are reshaping the manufacturing landscape, the G-Class stands as an example of how artisanal skills still hold tremendous value. This blend of traditional craftsmanship and modern precision engineering is particularly evident in the G Manufacture program. Here, customers can personalize nearly every aspect of their G-Class, from more than 30 exterior paint killers to a wide range of leather hues, stitching patterns, interior trims, and wheel designs. If a buyer wants orange leather with green piping and a matte olive exterior, they can have it. These builds are not separated into another facility. They're integrated into the main production line with designated bays where craftsmen apply these one-off features by hand. This level of customization presents huge logistical challenges, matching materials to build slots, keeping non-standard parts in stock, and maintaining quality across thousands of permutations. Yet the factory has embraced this complexity as a way to deepen the bond between owner and vehicle. Meanwhile, let's not forget the rigorous quality control that continues to influence every element of the G-Class's construction. For example, every powertrain used in the G-Class, whether the twin turbocharged V8 in the AMG variant or the inline-6 in the standard model, undergoes cold testing prior to installation. In cold testing, engines are spun up using electric motors without firing them, while sensors measure oil pressure, bearing resistance, valve timing, and sealing. This ensures that only powertrains meeting exact tolerances make it to the assembly floor. Similarly, each differential assembly is bench tested for noise and balance before integration into the vehicle. It's not enough for components to fit. They must perform to exacting standards. Even paint color undergoes scientific scrutiny. After application, each painted body is checked using spectrophotometers, special instruments that detect even the slightest variation in hue, brightness, and saturation. This is especially important when replacing panels after damage or repair. Consistency in color across different batches of paint and lighting conditions is notoriously difficult. Yet, Mercedes insists on millimetric perfection, even for colors that might only be chosen by 1 in 1,000 customers. It's this obsessive attention to detail that makes the G-Class stand out, and it's why its production process is stretched over more than 100 hours per vehicle. Where other vehicles are designed for efficiency, the G-Class is designed for excellence. Every step, from welding to upholstery, from software calibration to final wheel alignment, is geared toward creating something more than just a car. It's a statement of what happens when engineering, tradition, and passion come together under one roof. The production of a Tesla vehicle begins long before any car takes shape on the assembly line. Deep within the vast expanse of a Tesla Gigafactory, a meticulously orchestrated sequence of processes brings together raw materials, robotics, and human ingenuity to transform aluminum, lithium, silicon, and countless other elements into one of the most advanced electric vehicles on the planet. From the first bolt of sheet metal to the final pixel on the touchscreen interface, every component is born of a vision rooted in automation, precision, and sustainability. We begin with the raw materials that will ultimately form the structural skeleton of the car. Aluminum coils. These massive, industrial-grade aluminum rolls are delivered to the stamping facility in pre-cut widths and are carefully inspected for thickness consistency, surface finish, and chemical composition. Tesla predominantly uses high-strength aluminum alloys for many of its structural components due to their lightweight yet durable properties. These alloys are crucial to achieving Tesla's performance goals without sacrificing efficiency or safety. As each coil is unspooled, it is fed into a massive blanking press, a machine capable of cutting large sheets into specific dimensions called blanks. These blanks, often the size of a car door or hood, are prepped for the stamping process, where one of the most visually dramatic parts of the car's creation takes place. The stamping area, often housed in its own building due to the sheer vibration and noise, is where enormous dies, precision-engineered molds weighing several tons, shape these blanks into panels that will form the body-in-white structure of the car. Each die is lowered into a stamping press, often a servo-driven press with forces exceeding 5,000 tons. These machines exert immense pressure in milliseconds, forming the aluminum blank into complex geometries. Multiple stages of stamping may be needed for a single panel, including draw, trim, pierce, and flange operations. After stamping, robotic arms lift and transfer the formed panels onto conveyor belts, directing them to a quality inspection zone where laser scanners and human inspectors check for warping, stress marks, or micro cracks. Any deviation from tolerance can compromise fit or function and is promptly rejected or reworked. While the body panels are being shaped, another process begins deep inside the battery cell manufacturing area. Tesla, being vertically integrated, produces many of its own lithium-ion battery cells. Raw materials such as nickel, cobalt, manganese, and lithium carbonate are transported into specialized mixing tanks where they undergo slurry formation. These slurries are spread onto copper and aluminum foils, which are then dried in a vacuum oven to form electrodes. Once the electrodes are prepared, they are calendared, flattened to precise thicknesses, and wound or stacked into cylindrical, pouch, or prismatic cells depending on the vehicle model. Each cell is filled with electrolyte solution and hermetically sealed in a dry room to prevent moisture contamination, which could compromise safety or performance. These cells are then loaded into battery modules using robotic pick-and-place arms, which align and connect the terminals with extreme accuracy. The modules are assembled into packs, which include integrated cooling channels, structural support, and electronic control units. These battery packs will eventually be installed into the vehicle's underbody, providing both power and structural rigidity. Back in the body shop, the stamped aluminum panels are robotically welded and riveted together to form the body in white, the term for the car's skeletal shell before any paint or interior components are added. Tesla employs a combination of laser welding, spot welding, and structural adhesive bonding to fuse panels together with minimal distortion and maximum strength. Hundreds of robotic arms suspended from overhead gantries work in synchronized motion, welding, clamping, positioning, all choreographed with software that can adjust in real time based on tolerances and feedback. Laser scanners constantly monitor joint integrity and positional accuracy, ensuring that each weld is correctly formed and precisely located. The body in white at this stage is a gleaming raw aluminum shell, unpainted but fully formed, with all major exterior panels in place, including doors, hoods, and trunk lids, which are often removed and processed separately for better access and quality control. The next destination for the body is the paint shop, one of the most complex and environmentally controlled areas of the entire factory. Before painting can begin, the aluminum body must undergo a chemical pre-treatment process that removes oils, residues, and impurities. This is achieved by submerging the body in a series of baths, alkaline cleaners, deionized water rinses, and ultimately a zirconium or phosphate-based conversion coating that promotes adhesion and corrosion resistance. After drying in an oven to eliminate residual moisture, the body moves into the electrocoating tank, or e-coat stage. Here, the entire shell is submerged in a bath of electrically charged paint particles, which uniformly coat every crevice and interior cavity, ensuring anti-corrosion protection even in areas never visible to the customer. The body is then baked in a curing oven to harden the coating and prepare it for the next layers of paint. The painting process involves multiple coats: primer, base coat, and clear coat. Each coat is applied in sealed spray booths using high-precision atomizing robots, which follow programmed trajectories to ensure even coverage. Advanced electrostatic spray techniques are used to minimize overspray and improve efficiency. After each coat, the vehicle passes through a series of flash and bake ovens to dry and cure the paint, creating the high-gloss finish Tesla vehicles are known for. Once painting is complete, the body heads to the general assembly area, where it begins to transform from an empty shell into a fully operational vehicle. But before any parts are installed, the body undergoes another round of rigorous inspections. Laser alignment systems, gap and flush measuring tools, and robotic probes verify dimensional consistency across every surface. Any discrepancies are flagged and corrected before proceeding. Simultaneously, thousands of components are arriving from various sub-assembly lines and suppliers, including the interior trim, seats, dashboards, glass, wiring harnesses, and powertrain modules. These parts are delivered using automated guided vehicles, AGVs, that navigate the factory floor using embedded magnetic strips or LiDAR-based systems, ensuring just-in-time delivery with minimal human handling. The interior assembly begins with the installation of wiring harnesses, which are laid throughout the vehicle like a nervous system. These harnesses, containing kilometers of wire, are clipped into designated paths along the floor, pillars, and roof. Robots and human technicians work together, ensuring connectors are correctly routed and terminals are securely fastened. Next, the HVAC components, dashboard structure, and infotainment systems are installed, followed by airbags, sound insulation, and seat frames. At each step, torque-controlled tools and digital confirmation systems ensure that every fastener meets the required specification. The vehicle's panoramic glass roof, a signature element of Tesla's design language, is then lowered into place using vacuum suction lifters and laser-guided alignment tools. A two-part adhesive is applied by robotic nozzles to create a watertight seal. The doors, previously processed separately, are reattached and calibrated to ensure perfect alignment and smooth operation. Tesla's frameless door design and automatic opening features require particularly tight tolerances and sensor calibration. With the interior taking shape, the vehicle proceeds to powertrain integration, where the battery pack, assembled and tested in a parallel process, is lifted by robotic jigs and bolted into the vehicle's underbody using a sequence of torque-controlled actuators. The drive units, whether dual or tri-motor, are then installed onto the front and rear subframes, connected via suspension arms and motor mounts that are pre-aligned using precision fixtures. With the battery pack securely mounted and the drive units in position, the vehicle is now ready to undergo one of the most critical transitions in the entire manufacturing process: electrical and software activation. While the car may appear nearly complete, it is still lifeless. No lights, no screen activity, no sensor communication. This stage, often referred to as initialization, is where the vehicle essentially takes its first breath. A technician connects a diagnostic interface to the vehicle's central computer, usually via a secure data port under the dash, and uploads the foundational firmware that activates the vehicle's electronic control units, or ECUs. Each Tesla contains dozens of ECUs distributed throughout the chassis, responsible for everything from motor control to autopilot systems, battery thermal regulation, infotainment, and safety monitoring. Tesla's approach to software architecture is notably centralized compared to traditional automakers. Instead of relying on fragmented systems developed by various suppliers, Tesla has developed an in-house software stack that enables over-the-air updates, real-time diagnostics, and direct integration between mechanical systems and the vehicle's neural net. Once the firmware is loaded, a cascade of subsystems begins to power on. The touchscreen illuminates for the first time. The instrument cluster boots up. Cameras begin streaming to internal diagnostics. Every sensor, switch, and relay goes through a self-check process that verifies communication with the vehicle's central gateway. Any issues, such as a disconnected wire, a miscalibrated radar unit, or a sensor failure, are immediately logged for remediation. At this stage, even something as minor as a single LED malfunction will halt the progression until it's resolved. Next, attention turns to calibrating the advanced driver assistance systems. Tesla's autopilot suite relies heavily on an array of forward, rear, and side-facing cameras, ultrasonic sensors, and radar or LiDAR, depending on the model and hardware iteration. These units must be precisely aligned within the bodywork to ensure accurate environmental perception. Calibration is not just mechanical, but also algorithmic. As the vehicle is rolled into a controlled calibration zone, a series of reference panels, patterns, and 3D markers are placed around the car. Cameras are activated, and software compares live imaging data against known coordinates to fine-tune the visual input. The system will not pass if even a single camera is slightly skewed or obstructed. Following this, the wheels and tires are mounted, another process where automation and precision intersect. Each wheel assembly, comprising the tire, alloy rim, TPMS sensor, and balancing weights, is prepared in an adjacent sub-assembly cell. Robotic arms select the correct wheel variant depending on trim level and mount it onto the vehicle's wheel hub using torque-monitored tools. Once installed, the wheels are not yet fully ready for the road. They must be aligned. Wheel alignment takes place on a dedicated platform, where laser or camera-based alignment tools measure caster, camber, and toe angles in real time. Adjustments are made on the spot using robotic wrenches that turn suspension bolts until readings fall within micrometer level tolerances. Proper alignment is vital, not only for performance and safety, but also for autopilot accuracy, as steering bias or drift could interfere with the vehicle's self-driving capabilities. Now we arrive at one of the most impressive parts of Tesla's assembly process: final assembly verification, and end-of-line testing. This begins with a full-body water intrusion test. The completed vehicle is driven, or in some cases, automatically transported, into a sealed chamber known as the water test booth. High-pressure nozzles blast the car from all directions, simulating rain, puddle splashes, and pressure washing. Sensors inside the cabin monitor for even the slightest moisture intrusion. Any leak, even a trace around the door seals or underbody joints, results in a stop and targeted repair. Once the vehicle passes the water test, it moves into dynamic testing. But before that can begin, it must first pass a rolling road diagnostic check. The vehicle is positioned on a set of rollers that simulate driving conditions. Here, Tesla technicians run through a wide range of operational checks. Motor response is tested across a variety of simulated terrain profiles. Regenerative braking systems are evaluated to confirm energy recovery rates match expected values. HVAC systems are activated to check for proper airflow, temperature regulation, and acoustic performance. Inside the cabin, the touchscreen interface undergoes a systems integrity test. Each menu, function, and button is activated in sequence. The infotainment system is tested for connectivity to Tesla's software servers. Navigation modules are initialized. Bluetooth and Wi-Fi antennas are pinged. Microphones and speakers are checked for distortion or static. The cabin camera, located near the rearview mirror, is tested for focus and response to light changes. The glove box, front latch, trunk motors, and window regulators are also checked for proper operation and speed. After static diagnostics, the vehicle is finally ready for its low-speed dynamic test. On-site test tracks, usually located adjacent to or within the Gigafactory premises, allow each vehicle to undergo a short but comprehensive road test. The driver is usually a trained Tesla technician who runs the car through a prescribed routine: acceleration from 0 to moderate speeds, emergency braking, tight cornering, and high-speed lane changes. This test evaluates suspension response, noise levels, steering feel, and drivetrain behavior under real load conditions. The vehicle's software continues to log performance data throughout the drive, flagging any anomalies. After returning from the test track, the car enters the final visual inspection area. Here, a team of human inspectors armed with light panels, bore scopes, and digital checklists reviews every visible surface inside and out. Paint quality is scrutinized for orange peel texture, swirl marks, or dust nibs. Panel gaps are measured by hand and with laser gauges. The interior is inspected for material alignment, stitching accuracy, and uniform texture. Every single button, vent, trim piece, and fixture is physically touched and verified. If the vehicle passes this multi-layered gauntlet of inspections, it moves into what's known as pack out, the final preparation area before shipment. Here, the car receives its VIN label, ownership documentation, and destination configuration. This is where region-specific software settings, navigation maps, and language preferences are loaded. The final battery charge is administered, usually to around 90%, before the vehicle is powered down and prepared for transport. Each Tesla is now ready to leave the factory, but even this step is a study in logistical precision. Automated systems coordinate the movement of completed vehicles from the final inspection bay to outbound logistics. Depending on destination, the vehicle may be loaded onto a covered rail car, placed into a secure car carrier, or transferred to a nearby delivery hub. RFID tags embedded in the vehicle identify it to tracking systems that monitor its journey to the customer. It is important to note that Tesla's manufacturing ethos is grounded in continuous improvement. Unlike traditional automakers that rely on annual model cycles, Tesla frequently changes its assembly lines in real time, updating hardware or processes based on production learnings, user feedback, and software improvements. This philosophy means that even within the same week, two identical models may have subtle differences in componentry, firmware version, or assembly methods. These continuous upgrades are made possible by Tesla's heavy reliance on vertical integration and factory-level data analytics. Every torque wrench, sensor, robot, and diagnostic station feeds data into a centralized factory control system. Engineers analyze this data daily, making adjustments to improve efficiency, reduce rework rates, and enhance vehicle quality. This feedback loop between digital twin modeling, live production, and field performance is one of the reasons Tesla has been able to scale quickly while maintaining product innovation. With the vehicle now fully assembled, inspected, and approved, it embarks on the final leg of its journey: delivery to the customer. Whether arriving at a showroom, a regional distribution center, or directly to a driveway via Tesla's direct delivery program, the finished product represents not just a vehicle, but the culmination of thousands of interconnected systems working in harmony, each with millisecond-level precision, each tuned for performance, safety, and the future of mobility. Once a Tesla vehicle has cleared its final inspection and receives its shipment authorization, the journey from the Gigafactory to the customer begins. Unlike conventional auto manufacturers, which often rely on third-party dealership networks and extensive warehousing chains, Tesla's direct-to-consumer delivery model has radically simplified and streamlined this phase. Yet, behind that apparent simplicity lies a highly coordinated logistical infrastructure, optimized to handle the massive volume of vehicles produced daily across multiple global factories. At this stage, the vehicle is routed into a specialized outbound logistics yard, a designated section of the Gigafactory site, or an adjoining facility engineered specifically for the staging, sequencing, and transportation of finished vehicles. Each car is tagged with a digital shipping label that contains its vehicle identification number, model variant, color, wheel configuration, destination, and special instructions such as left-hand versus right-hand drive. This digital manifest is cross-referenced with Tesla's centralized logistics control software, ensuring that each car is placed into the correct regional batch for dispatch. Automated tug vehicles, similar to those used in airport ground operations, tow trailers of Tesla vehicles into position. If the vehicle is destined for domestic delivery, it is typically loaded onto a car carrier truck designed to hold 7 to 10 units. These carriers are scheduled to depart in tightly timed intervals, with software routing each truck for the most efficient delivery path based on real-time traffic, weather, and destination inventory levels. For international shipments, the process shifts slightly. Vehicles bound for overseas markets are loaded onto rail cars or container haulers that transport them to port facilities. At the port, the vehicles are driven onto roll-on/roll-off ships, a type of cargo vessel with built-in ramps and internal decks specifically designed for transporting cars. Each Tesla is parked and secured inside the vessel, often alongside other vehicles of the same batch, in a configuration that minimizes offloading time upon arrival. Throughout this journey, every vehicle remains digitally visible to Tesla's logistics team. GPS tags, onboard cellular connectivity, and carrier integration systems allow real-time tracking from the moment the vehicle leaves the plant to the moment it is delivered to the end customer. This level of transparency enables Tesla to forecast delivery windows with a high degree of accuracy and proactively resolve issues like weather delays or customs bottlenecks. Meanwhile, Tesla's delivery centers and service hubs are preparing to receive the vehicles. These locations, often converted warehouse spaces or minimalist showrooms, act as regional fulfillment points. Upon arrival, each vehicle undergoes a final pre-delivery inspection. This includes checking tire pressures, topping off windshield washer fluid, confirming that the software version is current, and ensuring the paint and interior remain in pristine condition. The protective coverings applied during shipment, such as plastic seat covers and foam door guards, are removed, and the car is detailed for presentation. If a customer has opted for Tesla's home delivery option, the vehicle may be dispatched from the delivery center directly to the buyer's driveway using either a flatbed or a mobile technician. Tesla's minimalist approach to delivery day often involves minimal paperwork, since much of the ownership transfer process is handled digitally ahead of time. Customers sign final documents electronically, receive a tutorial on using their new vehicle via the in-car interface or mobile app, and are given access to Tesla's expansive digital support ecosystem. But delivery is not the end of the story. It's merely the handoff point between manufacturing and long-term ownership. Tesla's commitment to post-production support is tightly integrated into its digital platform. The same software and hardware systems that facilitated the car's birth on the factory floor now serve as tools for its ongoing evolution. Over-the-air updates are one of the most defining characteristics of the Tesla ownership experience, and they depend on a robust ecosystem of remote diagnostics, data collection, and machine learning feedback loops. Every Tesla on the road constantly reports anonymized performance data back to Tesla's servers. This includes battery health, motor efficiency, navigation anomalies, autopilot behavior, sensor readings, and even software bugs. Engineers at Tesla's headquarters use this data to refine algorithms, push updates to correct inefficiencies, and enhance safety features, all without the owner needing to visit a service center. This dynamic software lifecycle, enabled by the tightly coupled manufacturing and software teams, makes Tesla vehicles unique in their ability to improve long after leaving the factory. Meanwhile, Tesla's service infrastructure continues to grow alongside its production volume. Instead of relying entirely on traditional service centers, Tesla employs a mobile service strategy wherever possible. These service vans are equipped with diagnostic tools, replacement parts, and certified technicians who can perform a wide range of repairs or updates at the customer's location. The ability to diagnose and even preemptively fix issues before they affect the driver is rooted in the precision and data fidelity achieved during the original manufacturing process. Looking back toward the factory, it's important to understand how Tesla's architectural philosophy supports this entire life cycle. Every gigafactory is designed not just to build vehicles, but to serve as a data hub, a testing ground, and a self-improving machine. These plants are built with flexibility in mind, using modular assembly lines that can be reconfigured on the fly. Instead of fixed conveyor belts, Tesla often uses autonomous mobile robots and smart material flow systems that can reroute components or vehicles as production needs change. The Gigafactory floor is not one continuous line, but a series of interconnected stations. Each one is equipped with sensors, machine vision, and feedback modules that report into a central factory operating system. This system not only tracks current production metrics, but also simulates process optimizations. For example, if a torque reading at a robotic arm consistently falls within the low-end threshold, engineers can be alerted and update the robot's behavior before a quality deviation even occurs. This predictive control approach reduces downtime and increases first-pass yield, meaning more vehicles pass inspection on the first try without needing rework. Vertical integration plays a critical role in making this system work. Tesla doesn't just assemble parts, it manufactures many of them. From battery cells to electric motors, from infotainment chips to firmware code, Tesla has brought traditionally outsourced operations in-house. This reduces dependency on suppliers, shortens feedback loops, and allows the company to innovate rapidly. For instance, if a new battery chemistry is developed in Tesla's R&D lab, pilot-scale production can begin almost immediately within a section of the existing Gigafactory, without the need for third-party approval or infrastructure overhaul. Even Tesla's supply chain reflects this philosophy of speed, control, and adaptability. Critical materials like lithium, nickel, and cobalt are sourced through long-term contracts with mining operations. And in some cases, Tesla has invested directly in extraction or refinement operations. These materials are routed directly to gigafactories or regional production hubs, bypassing many of the bottlenecks that affect traditional automakers who rely on complex supplier tiers and international freight forwarding. This system is further enhanced by Tesla's real-time digital twin architecture, a virtual replica of the entire manufacturing process. Every machine, part, and process is mirrored in a digital environment that can simulate disruptions, forecast efficiency gains, and run hypothetical scenarios. Want to test how a new weld technique might affect throughput? The digital twin can simulate that change in minutes, allowing engineers to make data-backed decisions that translate directly into physical adjustments. Through all of these layers, physical infrastructure, software integration, vertical manufacturing, and delivery logistics, Tesla has redefined what modern automotive production looks like. It's not just about building cars, it's about building a system that builds itself smarter with every iteration. Every vehicle produced feeds data back into this system. Every manufacturing anomaly becomes a learning opportunity. Every software update enhances not just the product, but the factory's ability to produce the next one even better. What this means is that the Gigafactory isn't a static building. It's a living organism, a self-correcting, self-improving entity designed not only to produce cars, but to redefine what a car even is in the age of autonomy, electrification, and artificial intelligence. And at the center of this vision lies a carefully choreographed dance of machinery, people, data, and innovation, all working in harmony to create not just a vehicle, but a new standard for the global auto industry. Inside a Tesla Gigafactory, perhaps the most mesmerizing and defining visual is the near-symphonic choreography of robots working in harmony. Tesla employs tens of thousands of industrial robots across its global facilities, many sourced from automation giants like KUKA and FANUC, and many others developed in-house. But these aren't the slow, single-arm welders of traditional auto plants. These are high-speed, multi-axis machines operating in tightly coordinated clusters that resemble mechanical dance troupes, fast, precise, and relentlessly efficient. The bulk of these robots are deployed in the body shop, where raw stamped panels are joined to form the body in white. Here, multiple robot arms work within inches of one another, one positioning a panel, another applying structural adhesive, and a third completing a weld, without ever colliding. This level of spatial awareness is made possible by a digital supervisory system that orchestrates each motion path in microseconds. Each robot is fitted with a suite of sensors, including force feedback, proximity detectors, and sometimes even cameras, allowing them to adapt slightly if a panel is marginally misaligned or a weld point needs micro-adjustment. In many production cells, Tesla has implemented what are known as friction stir welding units, robots capable of joining aluminum panels without melting them. This technique, originally developed for aerospace manufacturing, uses a high-speed rotating tool that generates frictional heat to soften and fuse materials without introducing impurities or thermal distortion. It results in stronger joints and is especially effective for joining thick battery pack casings or high-stress structural nodes. But Tesla's automation does not end at the mechanical level. Surrounding the physical robots is a vast digital control infrastructure powered by machine learning algorithms that analyze every torque value, weld voltage, and robot movement. These systems compare every single action against historical data to identify patterns that may indicate future faults. For example, if a particular welding arm shows a slight uptick in motion latency or current draw, the system can schedule predictive maintenance before a full failure occurs. This predictive maintenance loop dramatically increases uptime and reduces unexpected halts in the production line. Complementing this robotic workforce is a carefully integrated human team. Contrary to the misconception that gigafactories are purely robotic, Tesla maintains a robust human workforce in areas where judgment, dexterity, or problem solving are still superior to automation. For instance, interior trim installation, particularly tasks involving soft materials like Alcantara, stitched leather, or delicate wiring, still relies on trained technicians who can feel for correct tension, align materials by eye, and make subtle corrections during fitment. Human workers are also essential during final inspection, dynamic testing, and exception handling. If a part doesn't meet specifications, or if a software glitch prevents a subsystem from booting, it's often a human specialist who diagnoses and resolves the issue. These employees are equipped with digital tablets linked to Tesla's internal manufacturing cloud. They receive live data feeds from the vehicle's onboard sensors and can pull up schematics, tolerances, and previous production history in seconds. Every fix they apply, every note they enter, becomes part of that car's digital footprint, a log that follows it forever, even into post-sale diagnostics. Tesla's approach to worker efficiency is also shaped by ergonomic engineering and cognitive load optimization. Workstations are designed to reduce repetitive strain injuries with tool arms that balance heavy equipment and lift assists for placing components. Augmented reality overlays are sometimes used during training phases, projecting digital guides onto surfaces to help new employees understand complex assemblies. Rotational schedules ensure workers shift between physically demanding tasks and more routine duties, helping prevent fatigue-related errors. As we dig deeper into the brain of the Gigafactory, we arrive at what is perhaps Tesla's greatest long-term differentiator: the use of artificial intelligence, not just in the vehicles, but within the factory itself. Tesla doesn't merely automate individual machines, it trains its factories to optimize themselves. This is achieved through a combination of real-time data ingestion, cloud-based analytics, and reinforcement learning loops. Let's take an example from the paint shop. Traditionally, robots follow predefined spray paths based on CAD data. However, Tesla trains its painting robots using vision-based systems that analyze each body shell in real time for curvature, panel orientation, and gap uniformity. This data informs dynamic adjustments to spray trajectory, nozzle pressure, and stroke timing. The result is more uniform coating, fewer touch-ups, and improved long-term finish durability. Or consider battery pack assembly. Each cell inserted into a module is monitored for voltage, internal resistance, and capacitance. Tesla uses this data to build a profile of every module's thermal characteristics. If a pattern of abnormal cell degradation is observed in the field, engineers can trace it back to the exact production batch, process variables, or even environmental conditions at the time of assembly. This data loop enables retroactive improvements to manufacturing conditions and helps refine pack longevity models for future software updates. One of the more futuristic systems Tesla is rolling out across its newer gigafactories involves swarm intelligence for material transport. Rather than fixed conveyor systems, Tesla uses fleets of autonomous mobile robots that navigate the factory floor using SLAM algorithms. These robots aren't programmed with fixed paths. They learn optimal routes in real time, adapt to obstacles, and communicate with one another to avoid collisions or bottlenecks. This approach allows the factory layout to be more modular and reconfigurable, supporting agile production and faster adaptation to new models or variants. Equally fascinating is Tesla's use of simulation environments for factory operations. Entire sections of the Gigafactory are mirrored in a digital twin, an exact 3D replica of the physical space and its processes. Engineers can run simulations to test new workflows, evaluate machinery upgrades, or even plan how to integrate a new vehicle platform without ever disrupting the live production line? If a simulated robot collision is detected, the system can suggest path modifications or sequence changes before real-world implementation. This same philosophy extends to Tesla's use of custom silicon chips. While best known for its full self-driving computer, Tesla also designs specialized hardware for internal factory use. These include image recognition chips optimized for high-speed defect detection, edge computing units for data processing at the machine level, and embedded control systems that allow more precise energy regulation in welding and curing ovens. This level of hardware customization provides Tesla with granular control over quality, energy efficiency, and process speed. Another compelling layer of Tesla's factory evolution involves environmental engineering. Every gigafactory is designed with sustainability as a core tenet. Rooftop solar arrays, on-site water recycling systems, and battery-powered internal logistics vehicles are just some of the components contributing to closed-loop manufacturing. The energy used to produce each Tesla vehicle is increasingly being sourced from renewable systems within the facility itself, dramatically lowering life-cycle carbon emissions. Tesla's focus on vertical integration again becomes critical here. When energy systems, battery chemistry, robotics, and software all originate from the same corporate ecosystem, coordination becomes exponentially easier. Design tweaks to the battery casing, for example, can immediately inform changes to the casting molds, welding fixtures, or software-based thermal models, without the friction of cross-company coordination. Perhaps the most emblematic symbol of this holistic integration is Tesla's gigacasting machines. These are among the most powerful aluminum die casting machines in the world, capable of creating entire underbody sections as a single solid piece. These machines, designed in partnership with Adidra, reduce the number of parts in the vehicle's chassis from hundreds to just a few, eliminating fasteners, reducing weight, and improving crash performance. Integrating such massive components into the production line requires not just physical reconfiguration, but software integration, supply chain alignment, and real-time QC adaptation, all of which Tesla is uniquely positioned to manage in-house. As we look at the sum of all these systems, robotics, AI, digital twins, human-machine interfaces, gigacasting, and energy-conscious infrastructure, it becomes clear that the Tesla production process is not simply a variation on traditional automotive manufacturing. It is an entirely new operating system for building cars. A platform, not just a plant. A fusion of machine intelligence, predictive analytics, physical innovation, and agile design thinking, all operating under a single cohesive philosophy. The Tesla Gigafactory isn't just where vehicles are built. It's where ideas are born, tested, scaled, and refined in real time. Where the boundary between hardware and software dissolves. Where every sensor, every weld, and every decision feeds back into a growing repository of knowledge that powers the next generation of vehicles, robots, factories, and systems. One of the most disruptive engineering breakthroughs in Tesla's modern manufacturing playbook is the integration of the structural battery pack, a complete rethinking of how the battery, chassis, and underbody of the vehicle work together. In traditional automotive design, the battery pack is a standalone component, an energy container bolted to the car's underbody. But in Tesla's structural pack architecture, pioneered with the 4680 battery format, the battery no longer rides beneath the structure, it becomes the structure. To understand the scale of this shift, we first need to explore the 4680 cell itself. Named for its dimensions, 46mm wide and 80mm tall, the 4680 cylindrical lithium-ion cell represents a significant departure from the older 2170 and 18650 formats. It offers 5 times the energy, 6 times the power, and reduces the cost per kilowatt hour significantly. But it's not just the size that matters, it's how the cells are built and what they enable downstream in manufacturing. Each 4,680 cell is designed to support tabless internal architecture. In conventional cells, current must travel through a tab, a narrow conductor that can create resistance and heat. In Tesla's tabless design, the entire edge of the rolled electrode acts as a current collector, enabling more uniform heat distribution and higher current throughput. This drastically reduces internal resistance, improves efficiency during charge and discharge, and simplifies thermal management, a critical benefit when assembling high-density battery modules. These cells are produced in a vertically integrated line that starts with electrode slurry mixing, followed by coating, calendaring, cutting, and winding, all performed under strict environmental control. The wound jelly rolls are inserted into steel canisters, filled with electrolyte, sealed by laser welding, and then aged, tested, and sorted. What's remarkable is that Tesla's battery lines are not just production machines, they are learning machines. Each stage of battery cell production is heavily instrumented, with sensors that track viscosity, coating uniformity, line tension, and thermal behavior. These metrics feed back into AI-driven quality control systems that adapt in real time, reducing scrap rates and improving yield without requiring line shutdowns. Once the cells are complete, they are no longer assembled into modules as in traditional EVs. Instead, Tesla places them directly into the structural battery pack housing, eliminating intermediary module structures. This pack is a part of the vehicle's load-bearing frame, not an add-on. The cells are bonded in place using structural epoxy, and this bonded matrix provides rigidity akin to an aircraft's wing box design, a technique borrowed from aerospace engineering. A critical enabler of this approach is the use of high-performance structural foams and thermal adhesives. These materials serve multiple functions simultaneously. They manage vibration and noise, conduct heat away from the cells to integrated cooling loops, and crucially, form part of the vehicle's crash energy management system. During side or front impacts, the structural battery pack helps distribute forces across a wider area, reducing localized deformation and improving occupant safety. In the Gigafactory, structural pack assembly is a distinct line physically separate from standard battery operations due to its unique tooling requirements. Cells are loaded into the pack casing using high-speed robotic insertion machines. Adhesive dispensing systems apply precisely metered quantities of 2-part epoxy at high pressure. Once cells are in place, the entire structure is cured in massive industrial ovens that bring the adhesive to full mechanical strength. After cooling, the pack undergoes precision machining to create interfaces for the drive unit, seat mounts, and body attachment points. What results is not just a battery, it's a central element of the vehicle's physical frame. The top of the pack often serves as the interior floor of the cabin. The bottom, reinforced by ribbed aluminum or composite materials, acts as the underbody and aerodynamic tray. By combining energy storage, structural support, and crash safety into a single unit, Tesla eliminates dozens of separate components, reducing mass, simplifying manufacturing, and slashing costs. Now, integrate this with another innovation, gigacasting. Tesla's use of giant aluminum die casting machines to form the front and rear underbody sections of its vehicles is nothing short of revolutionary. These Idura Giga Press machines, weighing over 400 tons and applying clamping forces in the range of 6,000 to 9,000 tons, can create entire frame sections as a single cast. Instead of welding together hundreds of stamped components, Tesla now forms massive structural elements in one shot, lighter, stiffer, and far faster to produce. When the front and rear castings are combined with the central structural battery pack, Tesla essentially builds the entire underbody of a vehicle using just 3 large parts. These unibody trios replace what was once over 300 parts in older chassis architectures. This not only reduces complexity and assembly time, but also minimizes the number of suppliers, welds, fixtures, and potential quality defects. Each casting is inspected via X-ray and ultrasonic imaging to detect porosity, cracks, or incomplete fills. Any anomalies are rejected and remelted, maintaining a closed-loop aluminum recycling system. This radical simplification also redefines how the rest of the car is built. Traditional automotive factories are organized around a highly linear body-in-white process, frame construction, then floor pan, then underbody integration. Tesla's method is more like assembling a modular aircraft, where large sub-assemblies are brought together at fewer, more tightly controlled junctions. This allows Tesla to create more compact factories with faster cycle times and fewer workers per unit produced, metrics that directly impact capital efficiency and return on investment. To support these next-generation designs, Tesla continues to invest heavily in materials science research, much of it focused on high-strength aluminum alloys, advanced polymers, and die-casting feedstock refinement. The development of proprietary aluminum alloys that combine excellent flow characteristics in casting with high tensile strength post-treatment is a crucial part of making gigacasting work. These alloys must cool evenly, avoid brittleness, and withstand both crash loads and environmental exposure over time. In parallel, Tesla is exploring dry electrode manufacturing for future battery lines, a technique that eliminates the solvent-heavy coating and drying stages currently used in electrode production. Dry electrodes can be applied directly to the current collector using pressure and heat, significantly reducing energy consumption, production footprint, and cost. This aligns with Tesla's vision for more sustainable, vertically integrated gigafactories, ones that consume fewer resources per gigawatt hour and can be rapidly scaled in new geographies. Indeed, Tesla's goal is not just to build more cars, it's to scale manufacturing like a technology company, not an industrial one. This means shorter ramp-up times, smaller capital expenditures per unit of output, and a globally unified software-hardware stack that can be deployed anywhere in the world with minimal localization. Future gigafactories, like those planned in Mexico and India, are being designed with these structural pack and casting concepts at their core, meaning they won't just produce the next generation of Tesla vehicles, they will be born already optimized for speed, simplicity, and flexibility. This systems thinking extends even further into factory floor layout and material flow logistics. With fewer total parts, Tesla can implement straighter, more continuous material pathways, reducing the need for kitting, buffering, and material staging. Instead of having dozens of sub-assembly lines feeding hundreds of components, Tesla can deliver entire modules, like castings or packs, straight to the marriage station, where the vehicle begins to take its final form. This layout change reduces floor space, lowers error rates, and improves throughput. It also allows for greater software simulation of factory dynamics. When each vehicle only passes through 30 or 40 production cells, rather than 200 or 300, it becomes computationally feasible to simulate the entire factory in real time. AI-based systems can then test flow changes, balance labor loads, and reroute production if a bottleneck emerges, all before any change is implemented on the floor. The result is a self-learning, self-optimizing factory capable of adapting to demand shifts, supplier disruptions, or design updates faster than legacy automakers can retool a single line. All of this innovation, structural batteries, 4,680 cells, gigacasting, and software-first factories converges into a clear strategic objective: build more cars, better and faster, with fewer people and lower capital costs per unit. It's not about squeezing the last drop of efficiency from legacy systems. It's about replacing those systems entirely. And the boldness of that approach is why Tesla's manufacturing story remains one of the most closely watched industrial transformations of the 21st century. The creation of a Volkswagen Golf, one of the most iconic hatchbacks in automotive history, begins long before any metal is stamped or bolts are torqued. To truly appreciate the intricacy and precision of its manufacturing, we need to understand that this process represents the culmination of decades of engineering refinement, logistical coordination, and factory automation. It is not merely the assembly of components, but the orchestration of thousands of interdependent systems working in harmony, each with a dedicated role in transforming raw materials into a vehicle ready to roll off the line and onto the world's roads. The process begins at the heart of the operation, the Volkswagen manufacturing plant. One of the most famous Golf production facilities is located in Wolfsburg, Germany, where massive halls the size of several football fields stretch out in every direction. The atmosphere inside is clinical, controlled, and buzzing with quiet energy. Contrary to what one might expect, these spaces are not chaotic or deafening. They are meticulously organized, highly automated environments where human expertise collaborates with robotic precision to produce each vehicle to exacting standards. The first chapter in the physical birth of a Golf begins with the fabrication of the car's body shell. This process is commonly referred to as body in white, and it involves the welding and joining of raw sheet metal components that form the structural skeleton of the vehicle. These metal sheets typically arrive at the factory in pre-cut and coiled form, having been sourced from steel and aluminum suppliers who produce automotive-grade alloys with specific mechanical properties such as tensile strength, corrosion resistance, and energy absorption. Volkswagen has stringent quality controls on these materials, inspecting incoming shipments with laser scanners, chemical analysis equipment, and tensile testing machines to ensure that every roll meets the necessary specifications for forming and crash safety. Once approved, the metal sheets are uncoiled and fed into gigantic press machines, many stories tall, in what is known as the stamping area. These presses are a marvel in themselves, each capable of exerting thousands of tons of pressure. Using a combination of progressive and transfer dies, massive steel molds engineered to exact tolerances, these machines punch, bend, and form individual components like doors, hoods, roofs, floor panels, and side frames. Each die can weigh up to 40 tons and requires highly precise installation. The press line operates with the rhythmic certainty of a mechanical heartbeat, with each panel ejected onto a conveyor system that ferries it toward the next phase of production. From here, the stamped panels enter the body shop. This area is perhaps the most robot-dominated zone of the entire plant. Hundreds of robotic arms, painted in Volkswagen's signature orange or yellow, perform an intricately choreographed ballet of spot welding, laser welding, and riveting. These robots are guided by 3D coordinate programming and vision systems that allow them to make microscopic adjustments in real time. Their work is critical, as the dimensional accuracy of the welded body frame dictates how well later components, like the drivetrain and interior modules, will fit. The vehicle begins to take shape as floor panels are married with the side structures. Roofs are laser welded into place, and reinforcement beams are added to strengthen key impact zones. The welding robots are just one part of this highly automated process. In certain sections, human operators are still essential, particularly for tasks requiring dexterity, visual inspection, or adaptation to model variants. At these stations, workers equipped with pneumatic tools and ergonomic lifts work alongside the robots to install structural reinforcements, apply bonding agents, or verify alignment with laser-calibrated measurement systems. Every completed body shell is then run through a geometric measurement tunnel. where a series of cameras and lasers scan the surface down to the sub-millimeter level, ensuring that each vehicle conforms precisely to Volkswagen's quality blueprint. Once the body-in-white structure is completed and quality verified, the next transformative phase begins, the painting process. But before any color is applied, the raw metal body must be prepared to resist corrosion and adhere properly to the paint layers. The shell first passes through a cleaning and pre-treatment bath, typically involving a series of immersion tanks where it is cleaned of oils, particulates, and oxidation. This is followed by a process known as cathodic electrocoating, or e-coating. Here, the entire body is submerged in an electrically charged bath containing anti-corrosion primer particles. A low voltage current causes the primer to be drawn onto every metal surface, even inside closed box sections, providing complete and uniform protection. After e-coating, the body is dried in a curing oven and then transferred into the paint booths. These clean rooms are maintained at highly controlled temperature, humidity, and dust levels. The next steps involve the application of a primer layer, base coat, and clear coat, each sprayed using high-precision rotary atomizers. Robots again take the lead here, moving with fluid, sweeping motions to ensure a uniform paint film. Each coat is flash-dried between applications, and the final clear coat is cured in another high-temperature oven. Color accuracy and surface quality are assessed by specially trained technicians, often under special light tunnels that reveal even the most subtle defects or inconsistencies in the paint finish. With the painted body now cooled and cured, it proceeds to the marriage with the mechanical underpinnings, the powertrain, suspension, and chassis components. This phase marks the beginning of the general assembly process, which is one of the most logistically complex and human-involved areas of the plant. The painted body is mounted onto a continuously moving conveyor line known as the assembly line or production line, and begins its journey through a sequence of stations, each responsible for a specific set of tasks. One of the first major milestones on this line is the marriage station. Here, the body shell is carefully lowered onto a pre-assembled chassis, which includes the engine, transmission, front and rear axles, brake lines, fuel system, and other underbody modules. This process is performed using automated lifting gantries equipped with positioning sensors and torque control systems, ensuring that every bolt, mount, and fastener is attached with the correct torque specification. At this stage, precision is paramount. The alignment of engine mounts, suspension geometry, and drivetrain clearances are all verified using computer-aided fixtures and sensor feedback systems. As the car progresses down the line, workers and robots alternate in adding increasingly complex subsystems. Wiring harnesses, which have been pre-assembled in a separate part of the plant, are routed through the vehicle's interior and connected to key modules. These harnesses are essentially the vehicle's nervous system, containing hundreds of electrical wires that link sensors, control units, lighting, safety systems, and infotainment components. Routing these bundles accurately and securing them with clips, grommets, and tie wraps is both an art and a science, requiring a balance between accessibility, safety, and electromagnetic shielding. Following this, the interior components begin to enter the scene. Dashboards, HVAC units, center consoles, and infotainment displays are installed using guided insertion tools and laser alignment rigs. The seats, which are often built in a just-in-time fashion by a nearby supplier, are delivered directly to the line and bolted in place using high-torque pneumatic tools. Throughout this process, every module is scanned with a barcode reader to ensure traceability. This level of digital tracking allows Volkswagen to log the exact batch, supplier, and assembly timestamp for every major component, creating a complete digital twin of the vehicle's production history. By this point, the Golf has become instantly recognizable, with its iconic silhouette now cloaked in paint and outfitted with much of its interior. However, many critical systems have yet to be tested or activated. That next phase, electrical testing, fluid filling, and calibration, marks a turning point in the assembly process, transitioning the Golf from a mechanical object to a functioning machine. As the Volkswagen Golf continues its progression down the general assembly line, it begins to cross into one of the most critical sections of production: system initialization and functional testing. This stage transforms the vehicle from a silent shell into an electrically alive machine. It is here that the electronic control units, or ECUs, are first brought online. These digital brains govern virtually every function in the vehicle, from fuel injection timing and anti-lock braking response to climate control algorithms and sensor-based driver assistance systems. The Golf contains dozens of these ECUs, each responsible for different subsystems, and all interconnected through a series of high-speed data buses such as CAN, L-Line, and FlexRay. Before any electrical current is sent through the system, technicians connect the vehicle to a centralized factory diagnostic interface via a port located under the dashboard, the same OBD port later used by service technicians and inspection facilities. Using specialized software, factory workers upload the correct firmware and configuration data into the ECUs. This process is not merely about flashing software. It's about synchronizing every system to the specific build of that vehicle. Variables like engine type, transmission variant, lighting package, regional compliance requirements, and customer-selected options all influence how the ECUs behave. This digital handshake ensures the car will operate correctly and meet both performance and regulatory expectations. Once the ECUs are initialized, the next step is electrical verification. Automated test rigs are used to check that every connection, sensor, and actuator is functioning correctly. These rigs apply voltage and resistance checks through the wiring harness, lighting systems, and control modules. Even minor faults, such as an improperly seated connector or excessive resistance in a wire, are immediately flagged by the system. Any detected issues cause the car to be diverted from the main line to a specialized diagnostic bay where trained technicians perform pinpoint troubleshooting and rework, ensuring that no electrical faults go undetected. Parallel to the electrical system bring-up, the vehicle also receives its initial fill of operational fluids. These include engine oil, coolant, brake fluid, transmission fluid, power steering fluid if hydraulic, and in some cases, refrigerant for the air conditioning system. The filling process is performed by robotic dispensing arms that are pre-programmed to deliver the precise volume and type of fluid required for each model. Flow meters, pressure sensors, and digital records ensure absolute consistency and prevent underfilling or contamination. The fuel tank is also filled with a small amount of test fuel, typically around 5 to 10 liters, sufficient for initial startup, emissions testing, and short-range driving tests later in the process. After fluid filling, one of the most dramatic moments in the assembly process occurs: the engine start. This is not done casually, nor is it done without extensive prior checks. Once all systems are confirmed ready, a technician activates the ignition via the factory diagnostic system or a standard key fob, causing the engine to turn over for the first time. Sensors throughout the vehicle immediately begin transmitting data: engine RPM, oil pressure, coolant temperature, voltage levels, and emission sensor feedback, all of which are monitored live by quality assurance software. If the engine does not start within a certain time window, or if any critical values fall outside the permissible range, the vehicle is automatically flagged for further inspection. Assuming a successful startup, the next phase involves dynamic system checks. These include actuating key mechanical subsystems to ensure proper functionality. The steering is rotated lock to lock to test assist levels and detect any binding. The brakes are pressurized to confirm pedal feel and hydraulic integrity. The transmission is cycled through its gears, with automatic models shifting through each range while stationary, and manual models undergoing clutch engagement tests. Additional functions like power windows, central locking, infotainment screens, headlight alignment, and mirror adjustments are also verified at this stage. All of these checks are conducted on the moving assembly line or at dedicated inspection stations known as end-of-line testers. These stations are equipped with rollers, sensors, cameras, and feedback terminals that allow technicians to observe live data streams. If a vehicle passes all of these checks, it is allowed to proceed to the next major step: wheel mounting and torque application. At this point, the Golf receives its wheels and tires, which have been assembled and balanced in a separate part of the plant. Tire suppliers often work in close partnership with the assembly plant, sometimes even maintaining satellite facilities on-site to deliver tires in real time according to the production sequence. The wheels are mounted using robotic arms equipped with torque-sensing screwdrivers. These tools are programmed with model-specific torque settings and follow a defined tightening sequence to ensure that every lug nut is fastened uniformly, reducing the risk of vibration or uneven stress on the brake rotors. After wheel installation, the vehicle is lowered off its assembly jigs and finally touches the ground under its own weight. This moment, often called first contact, marks the vehicle's readiness for dynamic testing. It is now fully assembled, fully functional, and ready to move under its own power. But production does not end here. The vehicle is then driven, slowly and under tight controls, to the next area of the plant: the rolling road test bench, also known as the dynamometer station. Here, the car is placed onto a set of rollers that simulate driving conditions while keeping the vehicle stationary. The purpose of this test is to perform a full-spectrum functional evaluation under load. The vehicle is accelerated, decelerated, and driven at varying speeds, while sensors record engine performance, emissions output, braking effectiveness, and drivetrain behavior. Advanced vision systems check headlight aim and beam shape. Microphones measure cabin noise under acceleration. Even the wiper system is tested using artificial rainfall nozzles while the car is driven at simulated speeds. If any aspect of this test fails to meet Volkswagen's internal benchmarks, the car is again pulled from the line and sent to a rework zone. Here, highly trained specialists diagnose and resolve the issue, whether it be a misaligned sensor, a software glitch, or an out-of-spec component. Vehicles cannot proceed to final inspection until they achieve a perfect score on the dynamometer test. Following this dynamic validation, the car enters the final quality inspection area. This zone is brightly lit and staffed with quality control inspectors who perform a visual and tactile examination of every surface, seam, and feature. Paintwork is scrutinized under color-correct lighting to detect any blemishes, orange peel, or dust inclusions. Door gaps and panel alignment are measured with precision gauges. Interior materials are checked for fit, finish, and correct placement. Inspectors open every door, operate every switch, and sit in the car to check for rattles, uneven padding, or installation errors. This is often the first time someone interacts with the Golf as a complete product, and every detail matters. Once the vehicle passes its final inspection, a protective wrap is applied to its most vulnerable surfaces, typically the hood, roof, mirrors, and door edges, to prevent damage during transport. Barcodes and shipping labels are affixed, and the vehicle is driven to the logistics yard, where it joins a massive fleet of completed Golfs waiting for shipment. These yards are organized with incredible precision, with each car's location digitally tracked for efficient loading onto transport trucks or rail cars. While this marks the end of the physical assembly process within the factory walls, the story of each Golf is far from over. It now enters the distribution and logistics phase, a sprawling global network designed to deliver each vehicle to its final destination as quickly and safely as possible. But that segment of the journey involves a separate layer of logistical planning, international coordination, and dealership preparation, all of which merit a detailed explanation of their own. The freshly assembled Volkswagen Golf, now cloaked in its protective transport films and validated through layers of mechanical, electrical, and aesthetic inspections, begins its transition out of the factory environment and into the broader world. This stage, the post-production logistics and distribution process, is a sophisticated dance of real-time tracking, intermodal transportation, and region-specific compliance, all of which are critical to ensuring that each vehicle reaches the correct dealer in the correct configuration and in pristine condition. After final inspection, the Golf is driven from the assembly line to the Vehicle Logistics Center, often located adjacent to the main manufacturing facility. Here, trained drivers guide the vehicles along designated internal roads, maintaining low speeds and following strictly mapped routes to avoid cross-contamination or accidental damage. At the staging yard, vehicles are sorted based on destination markets, production variants, and transport mode. Some will head to domestic dealerships via truck, while others will be loaded onto trains for long-haul land journeys. For global markets, many Golfs are prepared for shipping by sea, making their way to port via specialized car-carrying rail networks. Before any Golf leaves the staging yard, a final scan is performed. Using handheld barcode scanners or RFID readers, workers verify the vehicle's unique VIN, vehicle identification number, against the factory's production records. This cross-referencing ensures that the car has passed all necessary quality gates, has been matched with the correct transportation order, and is headed to the appropriate regional hub. Additionally, certain destination countries require extra compliance steps before a vehicle can legally enter or be registered, such as emissions documentation, safety certification, or region-specific firmware updates to the vehicle's ECUs. These requirements are embedded into the logistics planning software, and vehicles are automatically routed to compliance zones where technicians apply the necessary updates or decals before departure. Once verified and queued, the Golf is prepared for loading onto a transport carrier. For truck transport, specialized vehicle haulers equipped with multi-level ramps are used. These carriers are engineered to accommodate various vehicle sizes while maximizing capacity and maintaining balance for road stability. Loading is conducted with extreme care. Each car is driven up ramps and secured using wheel straps, chocks, or integrated platform locks that prevent movement during transport. Drivers are trained not only in vehicle handling, but also in load balancing, ensuring that the distribution of weight across the trailer complies with legal road limits and mechanical tolerances. For long-distance rail transport, the Golf is moved onto enclosed or open-sided car transport wagons. These wagons can hold up to a dozen vehicles per unit and are designed to withstand the rigors of long-haul journeys across multiple climate zones. Rail is favored for its cost efficiency and environmental impact, particularly for routes within Europe, where dense rail infrastructure allows cars to be delivered to regional distribution centers with minimal handling. Once the vehicles reach their destination hubs, often located just outside major cities, they are transferred to final mile delivery trucks that ferry them to individual dealerships. When the Golf is destined for international markets outside of Europe, such as North America, Asia, or Australia, it must be transported by sea. This requires loading the vehicles onto large roll-on/roll-off cargo vessels, also known as ro-ro ships. These enormous ships are essentially floating multi-story parking garages, capable of holding thousands of vehicles at once. At the port terminal, cars are driven aboard by logistics personnel who work under tight schedules to fill each ship efficiently. Vehicles are parked according to a precise digital manifest, which maps each car's location by deck, row, and position for accurate unloading at the destination port. Ro-ro shipping requires a high level of environmental control. Vessels are designed to maintain safe humidity levels, minimize exposure to salt air, and prevent the movement of cars in rough seas through a system of tie-down points and loading jacks. Once the vehicle arrives in its destination country, it goes through a process known as port processing. This includes customs clearance, regulatory inspections, and any market-specific modifications. Depending on the country, this might involve the installation of alternative language infotainment software, the addition of local safety equipment like fire extinguishers or first aid kits, or the application of region-specific emblems and badges. Vehicles are once again inspected for transport-related damage, cleaned, and detailed before being sent to the dealership. But while distribution is an essential part of the car's journey, it is merely the final chapter in the broader industrial narrative. To truly understand the full scope of how a Volkswagen Golf comes to be, we must look beyond the visible car to the invisible infrastructure that supports its manufacture, the supplier network, component fabrication, and just-in-time logistics that converge at the assembly plant, like veins feeding into a living heart. Every Golf is made up of more than 30,000 individual parts, many of which are produced not by Volkswagen directly, but by a web of Tier 1 and Tier 2 suppliers across the globe. These include suppliers specializing in electronics, seats, glass, tires, injection molded plastics, turbochargers, radiators, axles, and much more. These companies operate under strict quality and timing requirements, often working within a just-in-sequence framework. This means that not only must the parts arrive just in time to avoid stockpiling or shortages, but they must also arrive in the exact order in which they are needed on the line. To enable this, Volkswagen uses a combination of supplier parks, regional distribution centers, and digital planning tools that forecast production demand down to the minute. Many of these suppliers operate satellite facilities on or near the Volkswagen campus itself. These microfactories are tightly integrated into the main production loop. For instance, a seat supplier may receive a digital order moments after a car body is painted and matched to a particular trim level. Within hours, the seat is built, quality checked, and delivered to the assembly line just as the car arrives at the station where it will be installed. The just-in-time system dramatically increases efficiency and reduces warehousing costs, but it also demands precision and resilience. Any disruption in the supply chain, whether due to weather, labor issues, or global events, can ripple across the production schedule. To manage this complexity, Volkswagen employs advanced manufacturing execution systems and enterprise resource planning software that communicate with suppliers, forecast demand, and adjust schedules in real time. Each supplier must adhere to predefined quality protocols, including statistical process control, failure mode analysis, and traceability documentation, which are routinely audited by Volkswagen's internal teams. On the component level, many key parts are manufactured using highly specialized processes before they ever reach the main assembly line. Take, for example, the engine, the mechanical heart of the Golf. Engine blocks begin their life as raw aluminum or cast iron, melted and poured into precision molds using high-pressure casting methods. Once solidified and cooled, the blocks are machined using CNC equipment that drills, hones, and surfaces the bores and mating faces to tolerances often measured in microns. Crankshafts, camshafts, pistons, and cylinder heads undergo similar processes, each passing through multiple heat treatment, grinding, and quality inspection stages before final assembly. The completed engine is then mated with its transmission, tested on a cold bench, a fixture that simulates operation without fuel or combustion, and sent to the main production hall. There, it joins the sequence of drivetrain assemblies that will eventually meet their respective body shells on the marriage line. Similarly, high-tech components like digital dashboards, ADAS sensors, and infotainment head units are built and tested in cleanroom environments to prevent contamination or electrostatic damage. These electronic assemblies are subjected to functional tests, environmental stress simulations, and firmware updates before being sent to the main line. At the plant level, all of these moving parts, mechanical, logistical, and digital, converge into what is often described as a cyber-physical production system. Assembly lines are increasingly governed by AI-enhanced predictive analytics, machine learning algorithms that forecast wear on machinery, and autonomous material handling vehicles that navigate factory floors using LiDAR and GPS. Real-time dashboards allow factory managers to monitor production flow, equipment uptime, part inventories, and worker ergonomics from centralized control centers. Robots, collaborative arms known as cobots, and human workers form a hybrid workforce that constantly adapts to changes in demand, variant complexity, or technological updates. All of this results in a manufacturing ecosystem that is as complex and finely tuned as the vehicles it produces. The Volkswagen Golf, which might appear to the average buyer as a simple compact hatchback, is in reality the output of a global network of suppliers, engineers, robots, and logisticians working in concert with millisecond-level precision. It is a product born of thousands of hands and millions of decisions, every one of them contributing to the moment when the car's engine starts for the first time, the headlights blink to life, and it begins its journey toward the showroom floor. As the story of the Volkswagen Golf continues within the factory walls, we now shift focus to the critical yet often overlooked phase that follows the assembly and functional testing of the physical vehicle. Final calibration, detailed software programming, and human-centered quality control measures that ensure not just mechanical soundness, but also driving experience fidelity, safety compliance, and brand consistency. This stage marks the final opportunity for engineers and technicians to refine the car's personality, the way it feels, sounds, and responds before it ever reaches a dealership. Once the vehicle passes its rolling road test, electrical verification, and cosmetic inspections, it enters what's referred to in modern manufacturing as the calibration and personalization loop. Here, technicians interface with the vehicle's multiple electronic control units, upwards of 50 in many Golf variants, to fine-tune parameters such as steering weight, throttle response, transmission shift points, air conditioning behavior, and even ambient lighting modes. Although these parameters are based on predefined model profiles, small adjustments are often needed to account for tolerances in component performance, environmental conditions, and the specific variant configuration of the vehicle. This process uses a digital toolchain, often referred to as a centralized vehicle configuration system. The technician connects a specialized programming console to the vehicle's onboard diagnostics port. Through this interface, the system retrieves the vehicle's build sheet, a digital summary of every major component, trim level, engine type, and region-specific setting installed during production. Based on this, the technician downloads the relevant firmware packages and configuration profiles from a secure Volkswagen server. These files include calibrations for dynamic systems like ESC, lane keeping assistance, adaptive cruise control, and the steering rack's servo control logic. The software installation itself is performed with high redundancy and validation steps. Each module receives a cryptographic checksum, ensuring the integrity of the code after download. The system then runs a diagnostic sweep, verifying that all ECUs are correctly communicating across the vehicle's CAN and LN bus architecture. Should any module fail to respond or report a checksum mismatch, the vehicle is flagged and removed from the main line for specialized reprogramming in a secure rework area. This level of rigor is necessary, not only to ensure reliability and drivability, but also because these software systems control functions directly linked to passenger safety. Following calibration, the vehicle passes through a sequence of human-led evaluations known internally as sensory audits. In a world increasingly governed by automated inspection and robotic precision, this human touch remains indispensable. Sensory audit teams, often composed of master technicians and experienced inspectors, evaluate things that machines cannot easily quantify. They listen for rattles or unexpected noises while operating various components, apply gentle force to test the feel of buttons and switches, and run their hands along upholstery seams to detect imperfections in fit or material finish. These teams test the firmness of seat padding, assess the resistance in climate control knobs, and verify the damping in the glove box lid's opening motion. This inspection process is not random. Each inspector follows a detailed checklist created for the Golf's specific variant, whether it's a base TSI model or a performance-oriented GTI. Every tactile point of interaction with the driver or passenger is scrutinized. The sound of the door closing, the feedback of the turn signal stalk, the clarity of the infotainment screen. Even the air vents are examined for smooth adjustability and structural integrity. These subtle, almost imperceptible qualities play a vital role in shaping customer perception. They influence whether a driver describes the Golf as solid, refined, or thoughtfully engineered. And Volkswagen knows that these sensory markers directly translate to brand loyalty. Parallel to the sensory audit is a final high-pressure water test. Here, the vehicle is driven into a sealed chamber where it is subjected to a simulated rainstorm, complete with directed nozzles spraying water at high pressure from multiple angles. The goal is to identify leaks around door seals, windshield bonds, taillights, and underbody grommets. As the water jets barrage the vehicle, sensors inside the cabin monitor for moisture ingress, while technicians inspect areas with flashlights and absorbent strips to detect even minute amounts of seepage. Any vehicle that fails this test is returned to a specialized sealing and bonding repair zone where issues are addressed before retesting. Once these final inspections are complete, the vehicle is officially released from production. However, in a modern Volkswagen plant, this release is also the beginning of a data-rich archival process. A complete digital profile of the vehicle, from every torque specification logged during assembly, to the paint batch number, to the firmware version of the braking system, is uploaded to a central database. This digital twin acts as a permanent reference for the vehicle throughout its service life. If a recall or service bulletin is ever issued in the future, this record allows Volkswagen to identify not only which vehicles are affected, but precisely what components or subsystems were installed and when. It is also worth noting that many Golf variants are produced with advanced driver assistance systems, which require a final calibration procedure using sophisticated optical targeting tools. This is especially critical for features like lane keeping assistance, traffic sign recognition, autonomous emergency braking, and adaptive cruise control, which rely on a front-facing camera, radar sensors, and sometimes LiDAR. These sensors must be calibrated in relation to the car's central axis, suspension height, and tire circumference. The calibration process is performed in a controlled bay using visual markers, checkerboard targets, and reference panels, positioned at known distances. Specialized software then guides the technician through alignment adjustments and performs a verification routine, simulating input data to test the system's reactions. The factory also considers the growing importance of software updates throughout a vehicle's lifecycle. Increasingly, Golf models are being built with over-the-air update capabilities. This means that certain vehicle functions can be improved or corrected remotely without visiting a dealership. To enable this, each vehicle must be registered with Volkswagen's secure update server and fitted with a telematics control unit capable of handling encrypted data downloads. Before leaving the plant, the vehicle undergoes a brief connectivity test using a private cellular or Wi-Fi network. This ensures that the vehicle can receive updates in the field and that the security keys assigned during factory programming are valid and authenticated. Another major focus of final stage production, particularly in recent years, is environmental sustainability. Volkswagen has implemented comprehensive measures to reduce the ecological footprint of Golf manufacturing. For example, paint shops, traditionally among the most energy-intensive and pollutant-heavy parts of vehicle production, now use water-based paints and advanced overspray capture systems to reduce volatile organic compound emissions. Waste heat from ovens and drying tunnels is recovered and recycled into the factory's climate system. Water used in the electrocoating and wash booths is treated on-site and reused in a closed-loop system. Powering the factory itself is a growing area of environmental emphasis. Many of the plants where the Golf is manufactured have transitioned to renewable energy sources, such as wind or hydroelectric power. In Wolfsburg, for instance, Volkswagen has partnered with regional utilities to supply the production lines with green electricity. Additionally, automated lighting, motion sensors, and energy-efficient drive systems on robots and conveyors contribute to reduced overall consumption. These investments not only lower the per-vehicle carbon output, but also align with Volkswagen Group's broader Way to Zero strategy, a commitment to climate-neutral mobility and carbon-neutral production by 2050. Within the plant, materials management is handled with sustainability in mind as well. Steel and aluminum scrap generated during stamping operations are carefully sorted, compressed, and sent to recycling centers, some of which are reintegrated back into the supply chain. Plastics from production offcuts or rejected trim parts are ground down and reused in non-visible components. Even packaging materials used to deliver parts, such as crates, dividers, and protective films, are tracked and returned to suppliers in a closed-loop logistics model. What makes the Volkswagen Golf's production so remarkable is not just the car itself, but the systems, philosophies, and technological ecosystems that produce it. Each vehicle embodies the cumulative effort of thousands of hours of engineering, years of supplier relationships, terabytes of design simulations, and millions of precisely orchestrated manufacturing movements. What rolls off the line is not a standalone product, but the physical representation of a global, highly optimized industrial organism. One designed to balance quality, efficiency, innovation, and sustainability in every nut, panel, circuit, and drop of fuel or electricity it consumes. As we move deeper into the Volkswagen Golf's manufacturing story, we begin to explore the systems behind the systems, the cutting-edge technologies and organizational strategies that elevate Golf production beyond traditional automotive assembly. Much of this innovation centers around Volkswagen's use of modular platforms, intelligent factory automation, and advanced data analytics, all of which have transformed not just how a Golf is made, but how efficiently, flexibly, and sustainably it can be produced, alongside a range of other vehicle models. At the core of this evolution is Volkswagen's MQB platform, short for Modulare Kurbaukasten, which translates to Modular Transverse Matrix. Introduced in the early 2010s, this platform underpins not only the Golf, but also a wide range of vehicles across Volkswagen Group's brands, including the Audi A3, Seat Leon, and Skoda Octavia. The brilliance of the MQB platform lies in its standardized architecture. Critical hard points, such as the position of the engine, the distance between pedals and front axle, and mounting locations for crash structures are fixed across models, while allowing flexible variation in wheelbase, track width, and body style. This enables massive economies of scale and allows the Wolfsburg plant, among others, to produce multiple models on a single line with minimal retooling. In practice, this means that a Golf might be built on the same line as a Tiguan or a Touran, using many of the same robotic stations, fastening tools, and software configurations. Tooling carts, parts bins, and robotic arms are designed with adaptability in mind. Instead of having separate jigs for each model, multifunctional fixtures and programmable robots detect the incoming body type via RFID tags or QR codes and adjust themselves in real time. A welding robot, for example, might apply different sequences or torque levels, depending on whether it is working on a Golf hatchback or a longer wheelbase estate model, all without human intervention. This production flexibility is supported by a sophisticated manufacturing execution system, a digital nervous system that tracks every car's status as it moves through the factory. Each vehicle is assigned a digital build order, stored in a centralized database and updated in real time. This build order contains detailed instructions for every station: which components to install, what software to flash, how to calibrate sensors, and which quality checks to perform. At each workstation, screens display the relevant data for the technician or robot, and barcode or RFID scanners confirm that the correct parts are being used before the system allows the job to proceed. The use of artificial intelligence and machine learning is increasingly embedded into this ecosystem. For instance, predictive maintenance systems monitor vibration, temperature, and performance data from thousands of robots, conveyors, and tools in real time. If a welding robot's arm begins to show early signs of wear, even imperceptible to human operators, the AI flags the issue and schedules preventative maintenance before failure can occur. This predictive approach significantly reduces downtime and helps maintain the tight production cadence that modern car manufacturing demands. Another area where AI plays a pivotal role is in vision systems and quality control. High-resolution cameras paired with deep learning algorithms are used throughout the assembly and inspection processes. These systems are trained on thousands of images to identify correct panel alignment, paint consistency, weld seam quality, and even minute cosmetic defects. In the paint shop, for example, the system can detect a single dust particle trapped in a clear coat, then alert technicians to isolate the cause, whether it's an air filtration issue, static charge on the body panel, or improper cleaning upstream. These insights are logged and used to refine both the hardware and the process over time, feeding back into a continuous improvement loop. But AI is not just about machines replacing human oversight, it's about augmenting human decision-making. In interior assembly, where more variation exists due to trim-level complexity, workers are assisted by augmented reality headsets that project assembly instructions directly into their field of view. These AR systems highlight where each clip, fastener, or electrical connector should go and can overlay 3D models of correct placements onto the physical work area. If the system detects a potential mismatch, such as a left-hand drive HVAC control unit being installed in a right-hand drive model, it alerts the worker before the part is fully installed. This not only reduces errors, but empowers technicians to handle more complex tasks without relying solely on memory or printed documentation. All of these advancements contribute to a concept Volkswagen refers to as smart production, an overarching philosophy that treats the factory not as a static facility, but as a living, evolving system. This philosophy is particularly evident in how Volkswagen manages its energy consumption, materials flow, and human ergonomics. For example, autonomous guided vehicles have largely replaced traditional forklifts and trolleys in many areas of the Golf's production. These AGVs navigate using a combination of magnetic strips, LiDAR, and real-time mapping, delivering parts from storage zones to the assembly line on demand. This reduces congestion, minimizes human error in part selection, and allows the line to adapt more fluidly to shifting production priorities. From an energy standpoint, smart production integrates intelligent building management systems that adjust heating, cooling, and lighting based on real-time occupancy and environmental data. Robots enter standby mode when idle for more than a few seconds. Compressed air systems, traditionally one of the most energy-intensive parts of any industrial plant, are monitored by AI that optimizes pressure delivery to exactly what is needed, exactly where it is needed, with zero excess. These micro-optimizations, when multiplied across thousands of systems and millions of cycles per year, contribute to measurable gains in sustainability. Ergonomics and human factors are also key to this philosophy. Every workstation on the Golf assembly line is designed to reduce strain, fatigue, and injury. Adjustable platforms allow workers to bring the vehicle to an optimal height depending on the task. Overhead, assist arms support the weight of heavy tools, reducing the need for muscle force. Color-coded part trays, automatic torque wrenches, and real-time feedback screens help workers maintain quality while minimizing the mental load of memorizing dozens of process steps. Additionally, Volkswagen invests heavily in worker training, offering digital simulators, VR-based assembly previews, and rotating task assignments to improve skill versatility and maintain high morale. This combination of human-centered design and intelligent automation also allows the Golf production line to be highly responsive to changing market demands. If a sudden spike in orders for a particular trim level occurs, say the Golf GTI with a sunroof and adaptive suspension, the MES system can reprioritize the build queue, notify suppliers of increased part demand, and adjust the workstations along the line in real time. Robots recalibrate their movement patterns, AGVs update their delivery routes, and workers are presented with new instructions through their digital displays. What once would have required days or weeks of retooling now happens in hours, or in some cases, minutes. One of the most compelling outcomes of these systems is Volkswagen's ability to maintain quality parity across global production sites. Thanks to centralized data systems, a Golf built in Wolfsburg can be virtually identical in build quality and performance to one assembled in Puebla, Mexico, or Changchun, China. Volkswagen uses digital twins of its production equipment, virtual replicas that simulate and mirror real-world machines, to replicate best practices across all facilities. If a process optimization is discovered in one plant, such as a more efficient adhesive application method or a faster sensor calibration routine, that improvement can be tested digitally, validated, and then rolled out to other sites via secure updates to their MES software. All of these advancements are not just about building a better car, they're about building a better manufacturing system, one that is scalable, adaptable, and forward-compatible. This is especially important as the automotive industry transitions to electrification. The Golf, as of the latest generation, shares many of its production processes with Volkswagen's ID family of electric vehicles. While the ID 3 and ID 4 are built on a separate platform, MEB. The lessons learned from MQB production, including robot versatility, flexible logistics, and digital calibration, are directly transferable. In fact, many stations within the same factory can now switch between building a combustion engine Golf and an electric vehicle, with only minor tooling changes and software adjustments. Volkswagen's approach to production is ultimately one of modular intelligence, a blend of standardized hardware, reconfigurable software, and scalable systems that can evolve with the demands of new technologies, consumer preferences, and global regulatory changes. And in this sense, Every Golf rolling off the line is not just a vehicle, it's a node in a vast, intelligent, and continually learning machine.